Check, check. Okay, let's try this again. Good morning. I'm Marco Morazan. I'm chairing the scheme workshop this year. So if anything goes wrong, please blame me and complain to me. If anything goes right, thank the authors and thank the program committee. And on that note, I will call on Jason, who is chairing our first session.
We good? All right, thank you, Marco. Let's get going. I want to hear Olivia talk to us about visualizing why non-deterministic finite state automata reject.
All right. I'm Olivia Kempinski. I'm from Seton Hall University. This is joint work with Marco. And I'll be showing you a visualization tool that demonstrates why non-deterministic finite state automata reject a given input word. Before we begin, I'll give you a brief introduction. What are non-deterministic finite state automata? NDFAs are state machines that can be given an input word, and that input word is either accepted or rejected. An NDFA accepts a given input word if there's at least one computation that takes the machine from a starting configuration to an accepting configuration. A configuration contains a state and the unconsumed input. A configuration is accepting if two conditions are met. One, there's at least one computation that takes the machine from start to final state. And two, in that final state, the unconsumed input is empty, which means the whole input word has been consumed. Now, NDFAs can also transition to a different state without consuming anything on empty transitions. And that transition relation of an NDFA is not a function. Because of that, it's difficult for students to understand why exactly it is that a word is rejected. One input word can contain multiple computations because the transition relation is not a function. And some of these computations may not even consume the entire input word. Now, in traditional formal languages and automata theory courses, students are asked to design a state-based machine with pen and paper. That means there's no testing, and it can be difficult for instructors to determine the design. To this end, FSM has been developed, a domain-specific language embedded in Racket that lets students design, test, implement state-based machines. One of the important features of FSM is that non-determinism is already built into the language. This saves students a lot of time trying to implement non-determinism. Now, if a student wants to understand why a word is accepted, there is a configuration trace provided. However, for rejected words, there is no configuration trace, because that would be too complicated. The shortcoming encouraged the work I'm going to present to you today, FSM computation graphs that capture all computations on which a word is rejected. But before I'll show you the FSM computation graph, I'll talk to you about some related work. Now, generally, computations are visualized as part of a computation tree. In a computation tree, each path is traced separately. A node in a computation tree denotes a configuration. The configuration contains the state and the unconsumed input. Now, there are two shortcomings that can arise with the approach of using computation tree. One, the tree may become very large or even infinite. If you take a look at the leftmost branch of the tree, there is a state Q3 and a state Q1. In both these configurations, the unconsumed input is already empty, but there is a transition from state Q3 to Q1 that doesn't consume anything, and one from Q1 to Q3 that doesn't consume anything. Now, this branch will continue infinitely in the tree. The other issue is that students are tempted to look for differences between identical configurations simply because they occur in different parts of the tree. To this end, computation graphs have been developed. In computation graphs, a node still represents a configuration. However, one node represents one configuration. Now, this tames the visualization size. As contrast to FSM, JFLab is another system that implements NDFAs. In JFLab, the user is able to step through each path of a computation tree, and with each step, the visited configurations are added to this configuration trace. This NDFA consists of Q0, the start state, Q1 and Q2 are the final states, and the darkened states are those that have been added to configurations in the last step. Now, this is a very useful tool. However, the user doesn't know how any of these configurations have been reached. Besides, this trace grows large very fast. For instance, if the user wanted to step through the entire input word on 7 A's after 14 steps, this is the configuration trace returned. This is very complicated, and the user doesn't really understand why this word has been accepted. Another system that implements computation graphs is Gadayu. On the left is an NDFA transition diagram in Gadayu. Q1 is the start state, Q3 is the final state. On the right, you can see the computation graph for that NDFA on the input word BB. Now observe that node Q3 occurs in the graph 3 times, denoting 3 different configurations. This node denotes configuration Q3BB because it has been reached with an empty transition that doesn't consume anything. This node denotes configuration Q3B, and this node, if 2 B's are red, denotes configuration Q3 empty, which is the only accepting configuration. Now, the issue students could have with this computation graph, especially beginning students, is that students naturally associate a node with a state and not a configuration. So it may be confusing that node Q3 occurs 3 different times. Besides that, the nodes denote configurations, not states. That means that this graph is not a subgraph of the transition diagram, which means it could be complicated for students to understand how this came to be out of this. Now, FSM takes a different approach. In FSM, nodes denote states, which means the computation graph is only a subgraph of the transition diagram, which makes it easy for students to associate one with the other. But before I show you the computation graphs on FSM, I'll show you what it's like to program in FSM. For example, if we take deterministic and non-deterministic finite state automata, these are the constructors, make DFA and make NDFA. Both contain K, a list of states, sigma, which is a list of alphabet symbols, S, which is a single start state in K, F, which is a list of final states in K, and delta, the transition relation. Additionally, for DFAs, the student may provide an optional node-det argument, which when provided assumes that delta, the transition relation, is already a function. So it's not necessary to add a det state. These are the observers. The top ones each extract one component of the machine. SM type returns the machine type. SM apply, given a machine and a word, returns the result, since NDFAs always decide a language that's either accept or reject. And SM show transitions, given a machine and a word, returns the configuration trace, which I will now demonstrate to you in Dr. Racket. Okay. This is what it would look like if a student wanted to implement an NDFA. We have the constructor, make NDFA, and its components. A word is in this machine's language if it either contains an even number of A's or an odd number of B's. Now the function that returns the transition diagram is smgraph. The tests all pass. The first one is given the input word BB, which is not an odd number of B's, so that's rejected. The second one is given 1A, which is not an even number of A's, so that is rejected. The third one is given an empty list, which is an even number of A's, that accepts. And the fourth one is an odd number of B's, so that is also accepted. Now, this is K, the list of states. This is the alphabet. S is the start state, which is highlighted in a green circle. A and D are the final states, which are represented as double circles. This is the transition relation that consists out of transitions. Each transition contains a source state, the red element, and the destination state. For example, SMTA, the epsilon denotes an empty transition. SMTA would be this transition. And each transition is represented as an arrow in the transition diagram. Right, now we will give it, now we will try to look at a configuration trace for an accepted word. Right. Given the input word B, B is in the language, that is an odd number of B's. This is the configuration trace that is returned. It begins with the starting configuration, containing the start state and the entire input word. Now the machine non-deterministically moves into C, where it reads a B transitioning into D. In D, the unconsumed input is empty, and D is the final state, therefore this word is accepted. Now we will give it a rejected word, such as A. A is not an even number of A's. This is rejected. There is no configuration trace, because as we have seen in JF Lab, that trace can become complicated very fast, which is unuseful to work with for the student. That is why computation graphs are so important. They are the only tool in FSM that really explain the student why a word is rejected. Finally, I'll show you the computation graphs. The goal of a computation graph in FSM is to visually demonstrate why a word is either accepted or rejected. Now, for accepted words, all we need is one computation. However, for rejected words, we need to show that all computations reject. There are two main distinctions in these graphs. One is the highlighting of states. Regular states that are traversed on any computation are just simple black circles. Those states that are reached at the end of at least one computation are highlighted in crimson, like this B state here. The other main distinction is the adding of a dead state in the graphs when transitions are missing. This is a computation graph of a machine that has been given input word A, and this graph shows two computations. Both start in the starting configuration, SA. For the top one, the machine reads input word A and transitions into B. In B, the unconsumed input is empty, but B is not a final state, so that is rejected. If the machine transitions into A, now A is a final state, but the unconsumed input isn't empty. That is why the graph creates this fresh dashed edge into the dead state, consuming the next input element. In the dead state, the rest of the input can be consumed, which is why the dead state is crimson. Now, the student immediately sees none of the crimson states are final states. The word is rejected. The student can also tell that some of the computations have been consumed entirely, but are rejected because they haven't reached a final state. And then some computations have not been consumed, some words have not been consumed entirely. Now, these configurations we call NDFA Stukies. Stuki, it's a structure, and it stands for state and unconsumed input. The other structures that we have are edges. Edges are transitions that contain a source state, the red element, and a destination state. Now we have to distinguish between two types of edges. Those regular edges that don't indicate any highlighting. And then we have special edges, NDFA spedges, that indicate crimson highlighting for the destination state. The way those edges are generated is with a conditional. This conditional is part of a function that takes as input an NDFA Stuki, and then it searches the transition relation of the machine for applicable edges that it then generates into spedges or regular edges. Now, if the NDFA Stuki's unconsumed input is empty, then the only applicable transitions are empty transitions. Those become NDFA spedges, indicating the end of a computation. If the length of the unconsumed input is 1 and there are empty transitions, those become NDFA edges, since the input isn't emptied yet. However, if there are non-empty transitions, those consume the last input element, those become NDFA spedges. And finally, if the length of the unconsumed input is greater 1, then no transitions empty the input, and all transitions are just NDFA edges. And finally, I'll show you the graphs. All right, this is an NDFA. D is the start state. R and S are the final states. A word is in this machine's language if it either contains an arbitrary number of BAs or an arbitrary number of ABs. Right, now we will give it an input word that is accepted, such as AB. If the machine is given input word AB, it transitions into the bottom loop, reads an A, reads nothing, reads a B, and halts an S. That is why S here is highlighted in crimson. The student immediately sees the only crimson state is the final state, the word is accepted. Also, this computation graph is a subgraph of the transition diagram, so it's easy to understand. Now we will give it an input word that is rejected. All right. Now this graph shows 5 different computations that all reject. If the machine transitions to the bottom loop again, reads an A, reads nothing, reads a B, and the graph is highlighted in crimson. If on a separate computation, the machine also reads nothing and transitions into B, it could also hold in B, which is why B is highlighted in crimson. Now, if the machine moves into the top loop, it needs to read an A and R, but there is no applicable transition. That is why the graph creates this dashed edge into the dead state, consuming the A. And then the B and the A are read in the dead state. If the machine wants to read an A and D, the same thing happens. Or if the machine moves into S, reads the A, and now needs to read a B and A. Dashed edge into the dead state, and the A is consumed in the dead state. Now the student immediately sees none of the crimson states are final states, the word is rejected. The student also sees that some of the computations have been, some of the words on some, the word on some computations has been consumed entirely. On other computations, it has not been consumed entirely. Now the way we implemented this is with the function make NDFA CG edges. This function takes as input a machine and a word and returns a list of NDFA edges. This list is used to generate the graphs. Now, the body of the function consists of 4 helper functions that call upon another, and the way they do that is visualized in this linear flow chart. NDFA computation tree to CG edges is the function that actually performs the traversal tree to generate this raw list of NDFA edges. From this list, we then need to remove the duplicates. Then NDFA remove redundant edges and accept is the function that, when a word is accepted, trims all unnecessary edges to simplify the graph. And finally, NDFA remove duplicate edges. This function removes NDFA edges that are also NDFA edges. So in separate computations, it could happen that the same transition is an edge and a spetch. In that case, we remove the edge because that doesn't indicate highlighting. And like this, we avoid duplicate labels. Now the function NDFA computation tree to CG edges is the really important one because it traverses the tree. It takes as input 2 accumulators, 2 lists of NDFA Stukies. The first list is the Stukies to visit in the next step, which at the start is only the starting configuration, containing the start state and the entire input word. The other list is the list of visited Stukies, which at the start is just empty. Now the way that function works is by performing a level by level breadth first search traversal. We start with the starting Stuki, like we just saw. Then we search the machine for applicable edges for the Stuki. If there are none applicable edges that consume the next input element, the function creates one to the dead state. Then the next list of Stukies is found from these transitions. Then the next list of applicable edges, which is then appended to the other edges, and so on. This is the body of the function. It takes as input those two accumulators: to visit, the list of unexplored Stukies, and visited, the list of explored Stukies. There are two locally defined variables, new edges and new Stukies. First, we generate the list of new edges. The way this works is we take one of the accumulators, the list of unexplored Stukies, and to each of these Stukies, we apply the function add to edges. Add to edges is the function that contains the conditional that decides whether a transition is a regular edge or a special edge that we have seen before. Now, once we have generated this list of new edges, we generate the list of new Stukies. Now, these two Stukies have been visited, but we still need them in order to look at the state and the algorithm input so that it can be passed down to the next Stukie. But the really important thing here is visited. Visited is the accumulator that contains all Stukies that have been visited. If a Stukie is in this accumulator, it's not being added again. This avoids revisiting Stukies and the code possibly falling into an infinite loop. Now, if the list of new Stukies is empty, the list of new edges is simply returned. Otherwise, the list of new edges is appended to the recursive call of the function that now takes as input the new Stukies to explore in the next step, and appending the to visit Stukies to visited, making them now part of the visited accumulator. Right. In conclusion, we have shown you a visualization tool that is especially useful in showing why words are rejected. The important parts are that FSM traces the transition diagram because nodes denote states and not configurations. Now, crimson states indicate where at least one computation ends, and if in a computation not the entire import has been consumed, we create a fresh dead state. For accepted words, we trim all edges that aren't being used to simplify the graphs. Future work includes generation of such graphs for push-down automata and for Turing machines, and we'd also like to implement this in a classroom setting when the course is offered at Seton Hall in spring, and we'd like to gather some student feedback. If you're interested in this work, we will be releasing a book later this fall called Programming-Based Formal Languages and Automata Theory. Yeah, thank you for your attention. Any questions?
What she said, questions?
I thought you were asking a question.
Well, I want to let the audience go first if they've got them. Yes, sir.
Thanks. Hi, I'm Simon Peyton-Jones.
Yeah,
Did
I
you
know.
try using different tools on different groups of students to try to figure out whether the ones using your tools understood things or made more progress than the ones using these other tools?
Sorry, did you ask if we have asked students?
I didn't just mean ask. I mean actually, put them in like guinea pigs. Try them
Yeah.
out, put them in groups, and see whether they make more progress
That is the
using
plan.
your tools than others.
So we offer the course in spring, where we will have a lot of guinea pigs. That is exactly the plan.
Great. So you're going to do user studies,
Yeah.
essentially.
Yes.
That's really good. We don't do enough user studies in programming languages community, but students are a good vehicle. Right? They're easy to get hold of in large numbers.
Ryan Steele. What did you use to generate the graphs? Was it GraphViz or was it something else entirely? I mean, how you actually showed the diagrams on screen. What tool was used under the hood there, if you know?
It was GraphViz, right?
Was it GraphViz? Okay.
Yeah.
Do we have other questions?
Yeah. Hi, nice talk, thank you. So maybe related to that, actually, is there any way to keep the layout of the graph as you do the transformation?
Sorry?
To keep the layout of the graph, so like the transformed graph you show with the computation traces to have the same layout as the one that you showed in the input. Because as I saw it, it got flipped and some of the states were moved. So
The layout.
yeah, like where the nodes are placed, right? Like the shape of the graph. Is there any way to keep it as you transform it?
Yeah, so in the order those edges are generated, they're being added. It doesn't really matter because these graphs are always nice.
Yeah.
Unfortunately, graph is automatically decides how it gets.
Right. I see. I see.
So that we don't have control.
I see.
You
All
can
right.
influence by choosing which edges to add first, but the way our function works is it filters, it's this function. NDFA remove duplicate edges. So it filters the graph, the list of edges to first add the regular edges, then the spedges.
Right. Thank you.
Question. So you remarked earlier that it's nice that your computation graphs are like a subgraph of the original thing, right? But that's conceptually simpler in some ways. But of course, the trade-off is that one node of your computation graph actually stands for several different configurations with different amounts of input being consumed.
Yes.
Right? And that's confusing in a different way to students. So it might be interesting to see which was most confusing, right? To have computation graphs in which the configurations are unique in their state unconsumed input pairs, or ones where you've collapsed them.
Yeah.
They're both confusing in their different ways, aren't they?
Yeah, I guess it also depends on the length of the input word.
Yeah. Oh, right. You mean so?
Like if it's really short.
If it's a long word, then you get an awful lot of states.
Yes,
In it
like-
if you spread it out, but you'll still just have however many that.
Yeah,
there are.
like for example in Gedayu,
Yeah.
I love this graph, by the way, which Marco told me not to tell you. But this is a very simple
That's a
word.
very little one,
It's
yeah.
BB.
Yeah.
But as soon as the word becomes longer, I guess this could become more complicated.
Okay. Thank you.
Well, I'm going to take chair privilege and ask, I could imagine wanting to have both of those or some sort of a GUI feature where I can click and expand from the short version into the long version and back. Have you considered that level of interaction?
We have not, but we can consider that. More work, yay.
Other questions? And let me go check the internet. Anybody else?
Hi, I have a question.
Really?
I was wondering if it was possible to do like step by step, like generate the graph or tell the graph how deep it's supposed to look, or if you only want one step. Is it possible to control that?
So there is an execution tool in FSM. It's called SM Visualize, and it lets the student go step by. So you still have the entire transition diagram, but then the step that you take, it's highlighted in blue, the arrow, and then you can step through. However, that only works for accepted words, because again, for rejected words, that's too complicated, which is also what encouraged the generation of these computation graphs.
Thank you.
Okay, all right, let's thank our speaker.
Thank you. Yeah, I have to give you the microphone. All right, there you go.
Just put it where you want it. That side? Okay, we're good. Okay. Something? I talk louder than this usually, so I think we'll be fine. That? Okay. Okay, I'll try it. Oh, I think I broke it. No? You want to put it in the back pocket? There we go. All right.
How to turn on the mirror. Screen mirroring. Tiana's iPad.
No, that's not the screen mirroring we want.
Can you help me out with the?
I don't know which one is the.
Do you mind if I tap some of these?
You know what? I'm going to take this off for now. Or maybe not. Hold on. Just take this off. Thanks, girl. We're ready to go? Okay. 1 second. Is this in slideshow mode? Perfect. Okay. Let me just see if it works. Cool. Hello, everyone.
All right.
Oh.
Up next, Tiana Meinig is going to be telling us about visualizing a non-deterministic to deterministic finite state machine transformation.
Hello, everyone. My name is Tiana Meinig, and I'm an undergrad at Seton Hall University. Today, I'm going to be showing you a visualization tool for non-deterministic to deterministic finite state machine transformation. This is also joint work with Marco from Seton Hall University. So in formal languages and automata theory courses, a great deal of emphasis is placed on constructive proofs. These proofs are very important because they establish the equivalence of different computation models. Algorithms have been developed to transform one computation model into another. For example, NDFA to DFA, NDFA to regular expression to NDFA, so on, so on. Today, our focus is going to be NDFA to DFA transformation. Now, why this transformation? So many students struggle to understand this transformation because of all of its steps. It's easy to get lost because a student has to keep track of multiple things. The reason for this is that the DFA simulates all the paths in the NDFA. So that can mean, for example, one path in the DFA can represent multiple paths in the NDFA, or one state in the DFA can represent multiple states in the NDFA. Also important to note that one DFA step is commonly referred to as a superstate. Also, one DFA edge can represent multiple edges of the NDFA. Now you can see why it gets confusing for a student to keep track of all these things while executing it step by step. And our visualization tool solves all three of these by visualizing the addition of the DFA edges one by one, while simultaneously visualizing the corresponding NDFA edges. So before I start, I know Olivia already gave you an introduction to FSM, but I feel obligated to refresh your memory. So FSM is a domain-specific language embedded in Racket that students use to design state machines. And for today's presentation, the relevant machine constructors are going to be make DFA and make NDFA. So both of these constructors have K, which are states of the machine. Sigma is just alphabet. S is the starting state in K. F is a list of final states in K. And finally, delta is a transition relation, which in the case of a DFA has to be a function. Now, the student can provide the optional no dead argument, which if they do, the constructor assumes that delta is already a complete function and it doesn't create a dead state. We also have the observers. So the first 5 extract the components of these constructors. An SM graph given a machine returns an image of a transition diagram of the machine that we have designed. Now I'm going to demonstrate programming in FSM. So we're going to look at the following example of the machine that accepts all the words in a language that are either empty word, a word that starts with A and is followed by an arbitrary number of A's. I forget I have a pointer in my hands. And a word that starts with A and is followed by an arbitrary number of B's. Now, I'm going to display the transition diagram right away, so this all is a little easier to follow. So first, we have our list of states. So we have S, which is the starting state where input has been consumed, and it's highlighted in green. Then we have A, B, and F, which in this case are all final states. So if a word ends up in any of those states, it is the word in the language, and it gets accepted. So A accepts all the words that start with A and are followed by an arbitrary number of B's. B accepts all the words that start with A and are followed by an arbitrary number of A's, and F accepts empty word. Now here we have transition rules. So as you can see here, for example, if on S you consume an A, you can either end up in A or B, which implies non-determinism. So this is an NDFA. Now, most textbooks use the following NDFA to DFA transformation. So they start with an NDFA, and then they construct a DFA. So they construct it in a following manner. Here, K prime is a list of superstates. Again, a reminder, superstate is just a state in the DFA. So the list of superstates is constructed as a power set of K. Sigma prime is the same. S prime is the starting superstate, and it contains all empties of S, which just is all states reachable from S by empty transition. F prime is a list of final superstates, and they all have to be in K prime, and every superstate has to contain at least one state from the list of final states in the NDFA. And finally, delta prime is list of all transitions from a superstate to a superstate. So, bear with me. For example, if you have some superstate Q that contains some arbitrary state little q, and you consume a y, right here, y, you can end up in some state little p, and all of the empties of that little p. Now, all of the little p's that you can end up in, and all of their empties, when you put union of them, that's your destination superstate that you end up in. So JFlap is a visualization tool that has developed an NDFA to DFA transformation. And I already here have constructed an NDFA of the same machine that we just looked at that accepts the words that start with A, followed by an arbitrary number of B's, starts with A, followed by an arbitrary number of A's, or just empty word. I'm going to convert to DFA now and show you how JFlap tool works. So here we have Q0, which is the starting state of the constructed DFA. And as you can see here, we have 0 and 3, which are just the numbers of the corresponding states in the NDFA of the superstate. In other words, empties of S, which again is the starting superstate. And now we're going to expand this once. So we expanded this transformation on an A. So on an A in the NDFA, we can either end up in states Q1 or Q2, which here corresponds to these numbers 1 and 2. So this edge in the DFA corresponds to these two edges in the NDFA. Now, we can keep stepping through this, or we can just complete the transformation in one step. So this is the transition diagram that we get. Hold on, let me make it a little smaller. So all of these edges in the DFA correspond to certain edges in the NDFA. Now, this machine is relatively simple. So the transition diagram of the DFA is going to look pretty simple. But if we just do this and slightly change this machine, hold on, there we go. Got to click through it. So here we're going to add 2 empty transitions. So what I'm doing right now is I'm constructing an NDFA that accepts the words that are missing one of the letters of A, B, or C. So it's either missing a C, a B, or an A. A, B, B, C, A, C. Okay, cool. Now I'm going to convert. So instead of stepping through the entire thing, I'm just going to complete it in one step and show you what we get. This is our transition diagram. Now, a thing about JFlap is if you want to see any part of this computation again, so any step that you step through, you can't go backwards. You would have to do this, and then start again, and then click here, and then expand. So it takes a little bit of time to actually go back and see something that you might have wanted to see. So that is JFlap. Now, OpenFlap is a similar tool with slightly less functionalities, but the haphazard graphs remain a problem. So here again, I'm presenting you the transformation that most textbooks use. So what we decided to do is tweak this transformation a little bit for the following reasons. So what we're bothered with is this. So K prime is a list of superstates, and in this transformation, it is a power set of K. Imagine how many subsets of K you might have if you have a huge NDFA. That's so many superstates that don't even end up being used in the construction of the DFA. So instead of computing the power set of K and going from there, we are going to traverse the computation tree find the transition function that we're going to encode into the DFA and just take the superstates that we need. So our transformation is going to look something like this. So we have make DFA where K prime is the encoding of our superstates, and S prime is the encoding of the starting state, F prime is the encoding of the final superstates, and finally in delta prime you're going to see our superstate transition function. So I'm going to walk you through the transformation that we do on the following NDFA. So first thing that we do is we need to compute empties for each state of the NDFA. So we're going to start with S, for example. There's my pointer. So S with consume no input can only stay in S, so that we're going to note as an empty of state S. But for example, D, when consume no input, can either stay in D or go to S. So empties of D are D and S. And we're going to do that for all of the states in the NDFA. Now, there's our actual superstate transition function. So the way we do this is we start with empties of S. So our starting superstate is always going to be empties of S. And we're going to see where we end up when we consume all the possible input this NDFA can consume and take all of the empties as well. So S, starting superstate, on an A in the NDFA can go to A, B, and its empties. So empties of A and B on an A are just A and B. So we note that as our next superstate. On a B from S, we can't really go anywhere. So we're going to put empty, and this in our building DFA is going to represent a dead state. Now we take AB, the superstate that we created, and take that as the next superstate that consumes some input. So on an A from A and B, we can't go anywhere. So we're going to note that as a dead state, so as empty. And on a B, we can go to C, D, and empties of them, so S as well. And that's going to be our next superstate. Now we can keep doing that for CDS and for all the other ones until we start having repeated superstate, and that's when we know when we're done. And our last row is just going to be transitions from the dead state, which are always just going to be into the dead state. So another thing we can do is we can encode these superstates to make them more readable. So all of the superstates that we gathered in the previous table, we're going to name simpler names, and finally the empty one we're going to name the dead state. So from this diagram here, we end up getting this diagram. So these are the encoded superstates and the dead state that we have in the DFA, and these edges are all of the edges that we saw in our transition function in one of the tables. So in our visualization tool, we build two state diagrams at every step. The NDFA diagram is always fully displayed, and the DFA diagram is built one edge at a time. Now, a thing that we've done that's new is we can step backwards. So before I move on, I have to warn you. I had some misconceptions when I came to this conference. I thought everyone was going to understand everything I'm saying, and I realized I'm throwing too many names at you. So just whatever you see now, it's going to be catchy names. They all sound similar, but they all have different meanings. So just pay attention because we're going to be using them. So our NDFA diagram is partitioned into three color-coded subsets. We have hedges, which are highlighted edges. And these are the edges of the NDFA that go into constructing the edge of the DFA that we're currently building. So those are the corresponding edges of the DFA edge that we're building. Then we have fedges. Those are faded edges. They're faded out in gray, and those are the edges that have been used to build previous edges of the DFA that we built. And finally, we have bledges. Those are black edges, and they are yet to be used to build an edge of the DFA. So here are them all together in the same machine. So 3 fedges right here, and a hedge, and a bledge. Now I'm going to show you the visualization tool, and you're going to see everything way more clearly. Okay. There we go. So this is our visualization. As you can see, the NDFA transition diagram is fully displayed with empties of S highlighted because that corresponds to the starting superstate in the DFA. Here we see that the DFA just has the starting superstate when we start, same as in JFlap. But if we step One step through the computation, you can see that in the DFA, an edge has been built and a message is displayed of which edge that is. So we have FS on an A to AB. Now look at the NDFA. S, empty transition F, is now faded out because we're not using it anymore, but it has been processed. So it is a fetch. And S on an A to A or B is highlighted because these two edges of the NDFA correspond to this one edge of the DFA. So another thing that you might notice is we decided not to encode the superstates because we thought it would be important for students to see exactly which states of the states that correspond in the NDFA, which ones correspond to the superstate in the DFA. So we left that not encoded. So these two are still bledges because they have not yet been processed. But if we step again, so this edge, FS on a B to dead state, obviously leads to the dead state, but you can see that nothing is highlighted in the NDFA because in the NDFA there's nothing that corresponds to the dead state. But these edges are still faded out because we're done with them. And these are still bledges because we haven't processed them yet. We can just keep stepping one by one, or we can complete in one step. We can complete this transformation at any point of the transformation. So this is a fully displayed DFA diagram. We're still going to get a message with the last edge that has been added. In this case, this is this B on a B to B. And as you can see, the corresponding edge, B on a B to B, is also highlighted. Everything else in the NDFA is a fetch now because they're all processed. The entire DFA diagram is built. And there is no bledges anymore because we've processed everything. Now what we can also do is step backwards. So I just removed the B on a B to B edge that was highlighted, and the next to last edge becomes highlighted in the DFA. This one is to the dead state, so you're not going to see anything highlighted in this NDFA. But this edge that used to be highlighted in the NDFA is now faded out because we're not using it. We can step all the way to the back of the computation, so to the mere beginning. And we can just play around with the buttons. We can complete it right away, but that is the visualization. So this is our implementation. It's important for us to keep track of two things: processed edges and unprocessed edges of both NDFA and the DFA. Now these three are probably already familiar to you: fedges, hedges, and bledges. So fedges and hedges are processed edges of the NDFA, and bledges are unprocessed edges of the NDFA. UPedges are unprocessed edges of the DFA, and pedges are the processed edges of the DFA. I told you there's going to be a lot of names. And we keep all of this in a visualization state structure. So instead of bugging you with this big chunk of a code, I'm going to show you what happens with these processed, unprocessed edges in a more visual form. So when we move the computation one step forward, one edge from the unprocessed DFA edges becomes a processed DFA edge. So in this case, it's that edge, AB on a B to B. That one gets moved from unprocessed to processed edges. And in the DFA, every one step forward, it's always just going to be one edge moving from unprocessed to processed. In the NDFA, we have a function that computes corresponding edges of that edge, so hedges. It computes them and highlights them. And whatever we add to highlighted edges, we also add to processed edges. And bledges, again, every time we step forwards, we take away from bledges because they're unprocessed and we process the part of them. And we add to fedges because fedges are also the processed ones. If we move one step backwards, we just reverse everything. So in the case of the DFA, we just take away one edge from processed and move it back to unprocessed. See this one? This one has now disappeared because it went back to unprocessed. In the NDFA, we recompute hedges for this edge to correspond. We add back to bledges because we went step backwards, and we take away from fedges. And finally, when we complete the transformation in one step, there's no unprocessed edges in either of them. So for the DFA, everything is in pedges or processed edges, and in the NDFA, now everything is in fedges. Everything's faded out because we're done. There's no bledges, and these hedges are highlighted. Now, there is cases where the last edge of the NDFA, actually the last edge added to the DFA, might be the one to the dead state. So if that's the case, all of this would be faded out and nothing would be highlighted. So this tool is very useful for students because we can easily determine why the superstates exist. And we accomplish that by not encoding the DFA graph. So you can clearly track which superstate corresponds to which states in the NDFA. We can see how all the NDFA edges are being processed by color coding them. Again, edges, hedges, bledges. So at first glance, the student can see exactly which edges of the NDFA are using to build, which edges of the NDFA have been used to build, and which edges are yet to be used. And we can comprehend the development of this transition function, and we accomplish that by stepping one by one and breaking down the problem for a student to see the building of the DFA exactly how they would have probably done it. And again, we can move backwards. Okay, so this is an interesting thing that I've done the other day. I decided to run both JFlap and R visualization on the same machine. I chose a little more complicated machine, the one that I demonstrated in JFlap, and I decided to run both of them 10 times to see what I get every time I complete a graph in one step. So this is the first run for our machine on the left and JFlap on the right. This is the second run. This is the third run. Fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So as you can see, JFlap graph keeps changing with every completion, and our transition diagram stays the same. This is also because GraphViz has a great algorithm for placing these states. So thank you, GraphViz. And finally, our future work includes adding visualizations for other transformations and constructors. We want to stay consistent with this because from experience, we've seen that students work the best in a predictable environment where they know exactly what to look for, at least in tools that they're using in their education. So for transformations, we're going to focus on NDFA to regular expressions and regular expressions to NDFA. And for constructors, we're going to do closure properties under union, cleaning star, concatenation, et cetera. If you want to learn more about programming in FSM and the transformation, you can get this book. It comes out later in fall. It's called Programming-Based Formal Languages and Automata Theory. Hey, we don't know if anyone was late. And it's written by Marco. And if you want to know more about the implementation of our visualization tool, you can read our paper. Thank you for your attention.
Another great talk. I'm an outsider, so this is very useful to me. I've learned a lot. I noticed that both you and the first speaker used the term student as your user. Is there a reason why this wouldn't be useful for experts that are trying to debug their programs?
No, absolutely. Experts can use it, but the reason why we use the term student so much is because right now, most of the people that use FSM are Seton Hall students.
Sure.
So the experience that we have with people using it is mostly students and our classmates. We're using it too for our classes, so yeah, that's why we use the word student.
Okay, so it would be equally useful for
yeah, absolutely.
programmers in general.
Absolutely.
Great, thanks.
Thanks. You you described the development of the deterministic automata as a sort of step-by-step process. You can step forwards and you can step backwards.
Oh, I thought you told me to step forwards. I'm sorry.
No. So your visualization steps forwards and backwards, right? But in fact, each step you've chosen one particular input symbol to choose, right? So there's more of a branching structure. You could imagine the student exploring it could say, oh, what would happen if I consumed a bee next? Isn't that right? It's not really a linear sequence, is it? Or it doesn't need to be linear. At any point, you could make multiple choices. You'll always end up with the same machine in the end, but it would sort of show up in a different order. Is that right?
Well, as a student, I'd always rather have it structured, even though I can't control it, than have unlimited, especially someone who's learning it for the first time, than having full control over what appears next, but not really knowing how to use it. So I'm pretty sure we add the edges in the order of the transition rules that we write. So we still have some sort of control over it because the entire visualization implementation works based on the machines that we construct, so based on the transition rules that we write first.
But you can imagine that once a student had got used to how it went, they might be interested in the idea that, oh, well, if I explore these in a different order, I still get the same machine at the end.
Exactly,
and be
they
able
can
to
tumble
try
them
that
down
out.
if they want to. They
So
can.
it'd be great if you could, give them that control.
Yeah, I think they can do
on
that.
their second or third time through.
Sorry?
The reason to do it this other way is because our colleagues who study these things in cognitive learning say that the extraneous overload to learn how to use the tool has an impact. And so if you limit their choices, the extraneous the extraneous load is less. That's the real reason. But of course, one could imagine a different tool where you can pick.
This tool.
Yeah.
Once they've got the idea,
Yeah.
so their cognitive load is
Yeah.
down, they internalize that.
Yeah.
Then we can try something more efficient. Yeah. Just an idea. Exactly.
If I understood correctly, though, you all consume them in the order that they're written linearly in
Yeah,
the
exactly.
automata?
Exactly,
So you could
students-
also just go reorder your automata and get the same behavior.
It depends on them and how they design.
Yes.
Hi. Had a question. You can go backward in your visualization. I was wondering if you did like a clever trick, so you start from the state and you figure out how to go backward, or if you just record the state when going forward, then you just restore them. Well,
Okay, the
to
way
go
we
back.
go forwards and backwards, I was gonna put the code in, but it was too big, and it would just be in code overload. So the way we go forwards and backwards is that we keep moving. We have a list of rules that the student designed in their machine, so that's what we're working with, and we're moving them from process to unprocessed. Of course, we have some functions that compute what's highlighted to the correspondent edge and stuff like that, but mostly it's just moving it around between the two lists. So that's how we go backwards.
Okay, so you don't need to record the history and restore history. You can go back from the rules.
Yeah, and it's always going to be the same as once the student designs the machine, it's the same order of rules every time when you run it on that machine. If you retumble the rules, it's going to be a different order, but the machine is while the visualization is running, the order is going to be consistent.
That's cool.
Thank you.
Hi, thanks. Great talk. This tool, I think, would be super useful at other universities as well. Is there a place where we can find the source code, or would we find ways to implement it in the book?
Okay, so in our paper, we included the GitHub link for FSM and downloading of the full thing. I think this tool is yet to be implemented at FSM, but soon it'll be there. So, yeah, stay
Thank you.
tuned.
Just real quick, how did you get Graphviz to keep your layout stable? When I use it,
Graphviz
it
does
doesn't
that
do
by itself. It's awesome. Graphviz has a great algorithm for that. I don't even know what that algorithm is, but it's pretty cool. Never had a problem with Graphviz. Oh,
Other questions? And let me go check the internet.
might be a good tip. The way, I don't know how you use Graphviz, but the way I used it in this visualization tool is I always lay out the two functions, first to design nodes, and then I take that as an input, that graph, for the function that designs the edges. So I first create the nodes, and then I create the edges using that graph as input.
All right. I guess, again, chair privilege, I'm going to take the last question. It's really cool once I've got the DFA out at the end. Is there some way, either through the GUI or through the REPL, to save that? Because I can imagine wanting to now use this DFA with some other one in an epsilon transition and go through the process again.
I think we're working on that right now for the FSM Visualize. So we add this tool into FSM Visualize, but more about that a little later.
All right, let's thank our speaker.
Testing, testing, 1, 2, 3.
Okay, welcome back to the second session. So Douglas, is it, right?
Yes.
Will present us the Callisto scheme project. So the floor is yours, sir.
All right, great, thank you. This is a long meandering story in real time. It took 20 years to get here, but I'm going to try to tell it in shorter time than 20 years. The project is called the Callisto Scheme Project, and it's actually not just this particular implementation of Scheme, but some of the stuff that came after and around it. I have a colleague, in fact, my colleague Jim Marshall is the brains behind the outfit, but he is stuck on a tarmac in Newark, New Jersey. So apparently there's some big storms yesterday, so he never made it out. He would be doing part of this talk, but I will be trying to fill in, and so be kind to me. I'm not a programming language expert at all, and Jim has his foot in programming languages, but neither one of us are actually programming languages researchers, and I'll tell you a little bit more about that. So I want to go back, if I may, 20 years, and there was a project that Jim and I were working on right after we got our freshly minted PhD certificates, licensed to go out and do stuff. And we had both been working in cognitive science and AI, machine learning. And we immediately thought, we really need to work with robots. And 20 years ago, we thought, couldn't imagine like large language models that we see today, ChatGPT. We thought in order to have any kind of intelligence, you had to have a body. So you need to study robots. So we started this project called Python Robotics. And if you Google Python Robotics, there's a lot of Python and a lot of robots. But 20 years ago, this was a new thing, and it was sort of clever. It was a client-server architecture in Python that allowed students to write simple little brains that could connect to any kind of robot. And it contained a lot of stuff connected to AI, but it was probably the first implementation of a neural network in Python. But we were focused on the robots. And that actually led to another project that we ended up getting a grant from Microsoft Research, and because we were known for this Python robotics. And we were taking some of the sophisticated ideas of doing real robotics, but making it be easy enough to use in an intro class. So when I taught college, at Bryn Mawr College, the first day of class, we would pass out a robot to every single student. And a lot of students were, whoa, what is this? No one told me that this was a robotics class. But it's really intro to computer science with a robot. The one big problem was that it was Python only. And so we sort of thought, it's really not fair that just, you can only use these robots if you use Python. So we started another project about 15 years ago, and I'm only going to talk about this project briefly, but it was called Calico. And the idea is that we wrote these libraries for music, art, robots, and it could be used, these libraries could be used with a variety of different languages. And so we had this one interface, Calico, where you could write in Python, or you could write in a language like, this was something we created, a block-based language we called Jigsaw. And basically, if you implemented those 4 buttons at the top, new, print, save, and run, then that was a programming language in this system. And we really enjoyed this, and students seemed to enjoy it. It was, its own little IDE, so it lived in its own little world. But we had all these different languages. We had, back in the day, F#. I don't know if people are still working with F#. Ruby. And we weren't sure 20 years ago what was going to be the predominant language used in introductory computer science classes. Python was just becoming popular, and I was an advocate for Python, and I think it's a great language for teaching. But there were a lot of other ones, and this was Iron Python. All the system was written in C#. But there was a big gap in the set of languages. You might guess what that is. Scheme. And we were like, how can we come up with a scheme language that would fit into this weird little architecture where we had these libraries written in C#. So at the time, this was about 2007, there wasn't anything available that we could grab and use. So we set out on this mission to build a scheme. Now, why would we do that? Well, we weren't programming language people. We were, cognitive scientists that were interested in robots, but we were both at small liberal arts colleges, so we wanted to create this system that used Scheme. We love Scheme. We're both from Indiana University. We both got our PhDs there, but not in programming languages. Jim took a few more classes than I did. So we felt compelled, really, to do what we could 20 years ago to get Scheme into the minds of students. So our goals then were, it had to be written in C#. We're going to abandon that goal here in a second. But at the time, there wasn't anything. There were a couple of projects. There was something called Iron Scheme, and there was another one called Iron Lisp. These Iron languages were C#-based languages. And they weren't ready. They didn't fit our needs. But we knew that there was a pathway from a continuation passing style interpreter into languages like C or Python or C#. So we set on this trip, we were going to build it. And we had no idea how hard or how long it was going to take. And soon after on this pathway, we actually did get it working for C#, but then we transitioned to Python for a couple of reasons. So, and this might be old news to some of you, although not everybody has actually had a programming language class yet, even though I know that some of you are presenting on programming languages. So here's the basic process to that. First, you write an interpreter for Scheme, in Scheme, and then you convert it to this continuation passing style. Are people familiar with CPS? Okay, not everybody, but I'll show you an example in just a second. But if you write your interpreter in Scheme in CPS, then you can go through these transformations that are correctness preserving. Make sure you can still have bugs in your code, but if you do the transformation properly, then you can transform that into a data structures format. And then if you do that, you can convert that into a register machine format. And then, and those are pretty straightforward processes. There's a lot of complicated details, no doubt. And then the last bit is fairly simple. Convert the register machine. These are all in Scheme. So this is write a version of Scheme in Scheme, convert it to another version in Scheme, convert that into another version in Scheme, and then convert that to C# or Python. So I want to be really concrete about that, so I want to give you an example. So I'm going to use this little definition of sum. It's a little recursive function, but imagine that this is actually an interpreter. So this is a Scheme interpreter. So sum is going to stand in the place for an entire interpreter. So you write it, and it works, great. But what we want to do is, in the first step, is we convert that to a continuation passing style form. And I'm not going to go through the entire details here, but wherever you have computation to do, you write a little function that contains that computation. And so in all of these examples, I'm going to have a little starter program, and then it's going to call into this continuation passing style version. So this is sort of a little header on this to get started this process. And so then K stands for the continuation, and in these places you apply the continuation, and then this is a continuation here, these little functions. So this is pretty mechanical. It's hard, to get all of the, and if you have a programming languages course in this style, you'll oftentimes, one of the assignments will be, write this function in continuation passing. Has anybody had to do that? Okay. Some old schoolers and not yet. Okay, this is coming. So that's the first step. And, you learn that perhaps in a programming language class. What you don't typically learn is that how to take that and let's abstract it a little bit by turning these functions into data structures. And so what happens here is you see these little bracket cont1, cont2. That's the actual functions that have been moved someplace else. And I didn't include them here, but this is just the infrastructure for everything that goes around these little continuations that are defined somewhere else. But they're simple little functions. And so that's all you do here is you turn those functions into these little make cont and apply cont continuations. So pretty mechanical, straightforward. Then the next thing you do is you actually, two parts, instead of passing arguments to these continuations, you put the values of the arguments in these registers. And so, it's very sort of machine-oriented, sort of using the word register even is, something that's sounds like hardware. And it is. It's something that you can actually implement this in assembly language if you wanted to. So instead of passing in arguments to the continuations, you set registers, and then you just call the continuations, and they get their values. So you set them in the calling program, and then you get them when you are actually using them and getting ready to call your continuation. And then the second part of that is you get rid of the actual function calls, so you don't apply the continuation anymore. You introduce a new register called PC, and then you set what program comes next, the function comes next, and then you have this thing called a trampoline. And you just start it up here, and you start the trampoline up, and it sort of bounces between continuations. And it runs that. And at that point, you can really implement Scheme in a language that doesn't have any kind of fancy, even function calls, really. It can be something like assembly language. And then the very last step is, and it's pretty syntactic, mechanical transformation, is to just take that and turn it into Python. And once you do that, you have a full continuation, call CC, the whole shebang that's implemented in whatever target language you want. So we did that, and probably I asked Jim early this morning, thinking about what kind of questions you might ask Jim so I could ask him so I could answer you. One of the questions I asked him was, what was the hardest part of writing all of this code? And perhaps the step number one was the hardest. Not just writing all of this code, the interpreter in continuation passing style, but also, when you get to the end and you write some code and you run it, you might want like error messages, undefined variable in line 3, and that got really complicated in order to pass all that source code information along. Even like you have macros and things like that, you've got to carry all of that information. So Jim pretty much wrote all 6,000 lines of the continuation passing. Doesn't sound like too much code, actually. And this has got comments. It's not really lines of code. It's just that's how many lines were in the program. And that gets transformed into the data structures version, which has about 9,000, and then transformed into a register machine. It's a little bit more verbose. And then, strangely, the number of lines actually diminished in the conversion to Python. I'm not really sure why there are fewer lines. Maybe, I don't know. But what's interesting about this, we end up with 4 versions of the scheme that all work. You can run each one of those independently, and you can, in fact, test it on scheme code across the board. And that's really useful for debugging. First you want to make sure that your program specification for your language, the continuation passing style program, works, and you catch bugs there. And then you apply the transformation, and you run the same test program, apply the transformation, run it again. And then finally, in Python, you can try it and make sure it works. So I'm not going to talk too much, but there is a macro system in Callisto Scheme. It's not as powerful if you know Shea Scheme or Racket Schemes, either define syntax or syntax rules. This was a custom implementation that we wanted to make it so that users, students, and others could do macros, but neither Jim nor I understood the full complexity of the ... ellipses, which is really an expressive way of creating macros. But we didn't know how to do that. So we made a simpler system. And you can do some pretty complicated things, but not as easily as you can in some of the other macro systems. Sometimes you might have to write helpers. And it's definitely true that our macro system is not hygienic. So we made sure that all the macros that we use in the language were, but a user can create things that are not. So you heard this morning a lot of really interesting things about non-deterministic systems. And in the paper, if you want to go see, we actually built this into our version of Scheme, like you saw this morning. This is a slightly different use for non-deterministic systems. This is, you choose a color, you apply some constraints, and then you just list out the answer. So it's a really powerful programming style. And I'm not going to talk too much about that. That example has a couple of, one macro and another just wrapper around choosing a color. But you can try that out on a different map. And you can see, yep, you really can color a map in 4 colors. But what's perhaps more interesting, or not interesting, but probably useful, is this is a TensorFlow model written. Basically, this is just like Python code converted to Scheme. And so you have these this let star and a bunch of things defined, and then you create a model and you train it. Pretty simple. But what's really cool is because it's written, instead of just setting the optimizer to something, you use this choose operator, this non-deterministic operation, just says pick one. And so it picks one and you train the model. But sometime later in the future, you can say, let's run that again with different. This is sometimes called hyperparameter search or a sweep in machine learning. You want to run the same model with a bunch of different hyperparameters. So you just say choose, and nothing you need to do special. It will just go back and choose different values for those hyperparameters, run the model again, and you end up with more results. So really, beautiful, elegant way of doing what people do today in a really practical way, but taking advantage of that non-deterministic system. So this is something that, well, should be near and dear to the speakers that talked earlier today. They spent a lot of time talking about, how do you analyze, a non-deterministic FSA? Well, we didn't really think about that. We thought about, we were going from Python into Scheme and making just a generically useful system. So we have a stack trace. Now this isn't, this is Scheme, so there's not really a stack. But we pretend like, yeah, it can definitely grow and grow. And in fact, you wouldn't want to turn this on when you have an infinite, recursive function. But for students and perhaps other people that are, trying to debug their Scheme program that doesn't necessarily use, the non-deterministic aspects, you can just have a stack trace. And so for people, switching between Python and Scheme, this looks familiar. In fact, some people would look at that and say, oh, you implemented this in Python. Yeah, but that's not from Python. That's, we had to build that. This is written in the continuation passing style interpreter. So we had to do all that formatting so that it would get translated and eventually come out in Python. So one thing that's really cool when we got done, when we made the system so that if there are Python functions available, you can call them from Scheme. And I can talk a little bit later if there's time about the environment, the way this works. We still have the full contours of Scheme, but then there's a top-level environment of Scheme and then a fallback environment that's Python. And so if you don't find the variable that you're looking for, you will pop out on that very last layer. And if it's in Python, oh, well, I'll use that. So import NumPy, all it really does is put NumPy in the Python environment, just like in Python. But then you can call it from Scheme. And if you notice, here I'm creating a matrix 3D out of a bunch of nested lists. And lists, these are linked lists. And it works. And the same way, here's an example using matplotlib. If you're a data scientist, this is one of your daily tools that you would use. So importing this Python library, you call it and then you show it. And this pops up a window that we didn't have to do anything. This just worked right out of the box. Here is one where we had to do a little bit of work, and I'll talk about this later perhaps. This is a macro or a magic is what they call them in Jupyter. So this %plot inline, that says if you do have a plot, then put it inside the notebook. And so instead of popping up a window, it's in this document so you can share it, and that picture of the plot appears right there in the document that you're sharing. So how did that work? Well, it did take we had to do a little bit, but it was in general, not specific to any Python library. What we did was we made the con cell in Scheme, which is just a car and a cooter in a box. It's a linked list structure, but we made the cons class look to Python like it's an actual list. So when we pass in something to matplotlib or NumPy, it looks just like Python thinks it's a list. And so it's just like, oh, I'll take item 1 and 2, and what's the length? So it's not fast to treat a linked list like a list, but it only gets used when you're actually calling something into Python. And so this makes an amazing number of things work when you're calling Python code from Scheme. We do have some support for doing Python-specific things. There's a Python eval, Python exec. In Python, if you don't know, there's actually 2 different ways of evaluating things. You can have expressions and you can have statements. So you have to use different kinds of evaluation on them. We also made a define bang so that if you want to define something in the Python environment, you can do that. And also we have this cute little wrapper that you can take a scheme function of arbitrary complexity and you wrap func around it, and that turns it into a Python function that you can call. And it's just like the sum that we saw. It's the continuation passing style stuff with a little bit of header on that, so it can call in and call back and get the result back out. One of the other things that we did was, instead of building all these percent and percent commands in Callisto scheme, we actually worked with other people in the Jupyter environment to make all of these meta commands available to other languages. We thought it would be a waste if we put all these meta commands in just our scheme version, whereas you have another language, we want to be able to take advantage of these meta commands. So we spun those out into something that we called meta kernel. And this is really interesting magic. This PX is parallel execution. And this comes from the Jupyter world, the idea of having a cluster and being able to run things in parallel. But very easily, you can run scheme code in parallel. And it's not as complicated as some parallel programming systems can be, but it's very handy that just in a notebook you can mark these cells. I want this code to go to all of the nodes, and this one I want to just run locally. So it's, you can do some of that kind of thing in, say, Racket, but it can get pretty complicated, and there's different kinds of limitations. And this way, it's pretty straightforward. Simple, it's just like ship code out, run it in this environment, get the answer back, and then you can do something with it. I taught programming languages course at Bryn Mawr College for many years. And back in the day, there was the version that I had at Indiana, we had to implement scheme in scheme. And as a student, I will admit, I was a little bit confused for the first couple of weeks. I'm writing a language that I don't really know, and I'm creating an interpreter for a language that I don't really know. And you can kind of get mixed up in the layers. When I taught this myself, I thought, I'm going to do this slightly differently. Especially because at this point, Python is getting more and more popular, so students are picking up Python in other classes, other places. So I had them implement scheme in Python. So Python's a language I know a little bit, and so scheme is the odd duck out and has these weird semantics that don't exist in Python, and so this is a really nice way to teach that. And you can do it fairly straightforwardly in Python. And so what's interesting, though, is that now we have a scheme. We can actually do, so the first part of the semester, we implemented scheme in Python. Now they know scheme a little bit. So now let's actually switch languages. And what you can do pretty easily with Callisto scheme is that you can write scheme code that interprets Python. Now this is crazy because Python syntax is, that would take you years probably to implement a Python parser. I don't know, maybe you guys can do it better with your non-deterministic systems. But we cheated a little bit. And so you see the very top line is import AST. So because we can take advantage of Python libraries, Python has a library called the AST, Abstract Syntax Tree. And you can see it used here at the bottom, ast.parse. So that takes care of a lot of complexity, and it gives you back an abstract syntax tree that you can then write your interpreter in scheme using the Python AST. And so with just a little bit of code, you can start out and you can build a real Python interpreter in scheme. All right, so I think that I will probably leave this here. I will open this up for questions, and thanks.
Hi. To do the conversion between the scheme interpreter and the CPS version and the other ones, did you use automatic like tools to do it, or
Yes.
did you do it by hand? Oh,
No. So this is a development system. So you can actually use this in general. You can take anything that's written in continuation passing style and apply these transformers to it. And you'll get out, you take the CPS version, apply the transformer to it, you'll get a data structure version, apply that to another transformer to it, and you get the register machine, and then you apply another transformation to get the target language out. And this is all on our GitHub, Callisto scheme. If anybody's interested, it would be really interesting if somebody wanted to explore, a visualizer for non-deterministic FSAs or even deterministic ones. It would be really cool that, instead of having a backtrace here, to pop up a little diagram and say, you've got an error right here, and be able to explore that and say, where did that error come from? How did I end up here? What's the problem? Did that answer your question? Okay.
Great talk. Thank you. So I have, I guess, two questions in one. First one is why Python? And the second one is, can you apply this to other languages as well?
So why Python? I guess Python, because it's really such a rich set of batteries. Being able to do it on machine learning, being able, just the vast set of libraries that exist with Python, I think make it really interesting as a pathway from here to whatever you might be interested in. I think that's, originally it was in C#, which, did I mention we had funding from Microsoft? So I think I'm in the right town here to say that. So, having the implementation in C# made a lot of sense. Everything was open source. But I didn't really mention the speed of Callisto scheme. And you can imagine it does not run very fast. But I'm glad we did it in Python. It's not really functional to do the kinds of big computations that you do in Racket or in Shea scheme. But for this kind of environment, for exploring, testing things out, it's really quite useful. In same ways that Python is useful. Python's pretty slow. And then this system built on that, which is even slower than that. And you had a second part?
Well, it was, have you tried it? But I guess C#.
My dream is to do it in JavaScript. I think that would, it has a built-in just-in-time compiler. I think that would scream and would be a lot of fun to try that.
Yeah, it makes sense. Thank you.
Yeah.
Okay, this is sort of more of a general question. You mentioned that the students back then, the first robot they got was only in Python, and there was a lot of research still to be done for programming languages related to AI. Now, what about today? Is there still, how important is programming language research for AI? Is it even important at all?
I think so. I think there are so many unanswered questions. The original version that we had, that it was basically a hypothesis. Can you write a bunch of libraries, robots and music and art, and then have the students move between different languages using the same libraries, so keeping those fixed, but seeing how to do the same thing from different languages? That didn't go anywhere. We didn't get funding for it, so that was a bad idea. But I think there's lots of ideas in programming languages yet to be explored that we're really just now touching the tip of the iceberg. Yes, I'll be around, so all night. If you want to do dinner or something, we can talk some more. Okay.
Thank you.
Thanks. Oh, I got to give you this.
So next we have our keynote speaker, Christos. And this should prove to be an incredibly interesting talk because usually in programming languages we worry about correctness and about efficiency. But now we're going to look at how to study pragmatics. What does the practical programmer need? And how do we measure how well we're serving the needs of practical programmers? Okay, so when you're ready, Christos, the floor is yours.
Thank you. Just a moment. Okay, hi everybody. I'm Christos. I'm from Northwestern University. Thank you, Marco, for the introduction. And I'm going to tell you today about a project that I've been working on for the last 4 or 5 years, whose topic is a new method for evaluating what we call PL pragmatics. Okay? Of course, the first question should be, what do I mean by PL pragmatics? Often pragmatics is used to mean, pragmatic, but actually I have a more specific notion in mind. Okay? The idea of PL pragmatics actually goes way back in the world of programming languages. There is a seminal dissertation from 1968, Jim Morris's dissertation. It's in a context where people are still trying to understand what semantics means. So Jim Morris shows up and he says, we can borrow some ideas from the world of semiotics and linguistics. And if we want to talk about the various layers of programming languages, we can say that there is syntax, which is about the valid forms, what we can write down as valid programs. There is semantics, which is how these valid forms relate to each other and how they combine to give meaning to more complex forms. This is usually the intrinsic meaning of these forms that we can describe in the eternal language of mathematics. And then there is pragmatics, which is how the meaning of those words relates to the actual users. Something surprising happens after this analysis. In the next paragraph in the dissertation, Morris goes on to basically says, okay, we can reduce users to just the machine and what the machine observes. And here's the surprising part. He says, we don't need to care anymore about semantics. All we need to care is pragmatics, because all that matters is what the machine observes. And in the process, he basically equates pragmatics with operational semantics. From the perspective of semantics, this has a significant, it's a significant step, because he uses that as a building block to define what we call contextual equivalence, which has become the golden standard of understanding the meaning of programs and program fragments nowadays. But in terms of pragmatics, as I said, there is this reduction step. Basically, the user becomes the machine. Okay? In this talk, we are going to stick to semantics as being, the study of how we understand the meaning of pieces of programs, and also at the meta level, the properties of those programs, especially the theoretical ones, correctness and so on. But when it gets to pragmatics, we're going to take a more expansive view, again inspired by linguistics. In linguistics, the difference between semantics and pragmatics is that once you try to use a term in context, the context may modify the meaning of the term. And this is exactly what we're going to do for PL pragmatics. We are going to say that once you get a feature that has a specific semantics, when you place it in a work context, the value of that feature may change. Okay? And what I mean by work context, basically I mean things that we do as programmers and maintainers of programs, how easy it is to write code with particular features, how easy it is to debug it, and how easy it is to maintain it. Okay? And so on. So just to make things a little bit more concrete, a semantics question that we may want to examine is, how do, for instance, gradual type enforcement mechanisms work? What are their operations? What are their checks? What kind of error messages they give us when something goes wrong? Okay? A pragmatics question is, which of these mechanisms helps us, for instance, debug? Okay? By the way, if you have any questions, there is time at the end for questions, but I would prefer if we were a little bit more informal, so just let me know, okay? Don't hesitate to interrupt. Cool. So now that we have PL pragmatics, I hope we are all on the same page about what PL pragmatics mean. Let's move to the how. We're going to do this empirically, okay? And just to exclude the obvious possibility, this is not a user studies method, okay? Instead, I am going to present the rational programmer, which is basically a recipe for constructing large-scale automated experiments that we can use to examine the validity, the answers to questions about pragmatics, okay? So the first step in this recipe is that we pick a feature and some context to examine, okay? Let's say, for instance, gradual typing and debugging. Those two go together. All the time there needs to be a context when we're talking about pragmatics. Then what we do is we formulate a hypothesis. How is this feature going to benefit the developer in this particular context? This is a little bit vague, but the rational programmer actually asks us to do something a little bit more specific. It's not just about the how. We need to specify a use strategy. For instance, I'm going to use the gradual type system in a particular way in order to figure out where, let's say, a dynamic type violation, where is the root of such a violation, okay? Once we have the use strategy, the next step is to turn it into an algorithmic procedure, okay? This algorithmic procedure is actually the namesake rational programmer because it's an abstraction of a programmer working in that context to achieve a specific goal. Given this algorithmic procedure, we go and construct populations of scenario, let's say debugging scenario, for the particular running example of gradual typing and debugging. And then we can run a simulation. And from the data we get and we analyze, we can go back and examine our hypothesis, whether we refute it or validate it. Okay? So this is the pipeline. It's an instance of the scientific method, pretty much, with simulation at its core. I presented this as something that we can use. Oh, please stand behind the lectern. Sorry, I was moving too much. I presented this as something that we can use to examine a particular feature, but we can actually do the same for collections of features that have different semantics or even different features, as long as we are able to create multiple strategy variants, one for different features, so we can repeat this process in parallel, collect data, and compare the hypothesis for all the different features. Okay? I'll give you a more concrete example as we keep going. I want to say, though, that even though I made it look like a very streamlined process, there are significant challenges that someone needs to overcome in order to implement it. So we need to come up with a hypothesis, and in particular, a hypothesis that has a strategy at its core about how we are going to use the feature to achieve our goal. Then we need to turn this strategy into a procedure. And this is very tricky in some cases, because we are abstracting over a programmer. This often involves creativity. So somehow we have to take that creativity out of the mix in order to get an actual algorithm. And finally, we need to be able to create a significant population, a diverse population of scenario, so that we can draw from the simulation results that have some significance too. Okay? So, and of course, all these answers to all these problems depend on the specifics. It's very specific to the question we ask. So every time someone tries to do a new rational programmer study, they have to try to understand how to overcome these obstacles. And this is where the research part of working with the rational programmer comes in. Cool. I'm going to make all of these things that I just said concrete. And I'm going to talk about the running question, about gradual typing and debugging, and in particular, which gradual type enforcement mechanisms help us with debugging. Okay? I'm going to open a parenthesis. by the way, before I get to the parentheses, actually, this is work that I have been doing with my student, Lucas Lazarek, in collaboration with Ben Greenman and Matthias Feleisen. It's a work in 2 parts, and actually, Lucas presented the second part of that work at ICFP earlier this work. In case some of you were there, I'm going to try to keep the overlap minimum, just to keep this talk self-contained. Lucas focused on the results and the data. I'm going to focus on the process. Okay? So, word scheme, so parentheses are okay. I'm going to open a parenthesis because I want to make sure that everybody is okay about what I mean about gradual typing enforcement mechanisms. Okay? And to do that, I'm going to talk about a small example. It's a simple example. We wrote an application. It consists of basically 3 different modules. One module is a library that we found, I don't know, somewhere in the Racket package system. Then we have a utils file that we also wrote. And finally, we have our main application file that uses the other 2. As we were working in this application, we noticed that we often do a bunch of silly mistakes, like passing the wrong kind of argument to a function. So we decided to take advantage of typed Racket and its ability to basically add types gradually to programs, to add sort of some types to certain parts of our program. So we created a type interface between the library and the main, and we also fully typed our own utilities little module. Okay? Here is how, roughly, I don't expect you to read the code. The important part here is that basically this is the library that we found somewhere in the package system, and this is the interface we wrote. Basically, the important part is that it says that we have a function exported JSON unpack that consumes JSON. It consumes a string and it gives us back a list of hash tables. Okay? What this guy does is reading the JSON object and then basically packaging it up iteratively in a list. Basically, it's a comprehension of a whole document. Our main file imports the interface so that it has access to the version of the library that is protected. And then it goes on to call JSON unpack with some file, and then calls also summarize edges that comes from our utilities library. Okay? Our utilities are fully written in typed Racket. There are types to basically say that user info, which is the data that we have inside the JSON file, has been marshaled into a hash table, basically, and that summarize edges accepts a list of these user infos, a list of hash tables, and then it does some aggregation. Okay? So far, so good. We can ask the type checker of typed Racket to inspect our program, analyze it, and it won't find any problem, because the way we use the types inside the typed module is consistent with the implementation of the code. However, what's going to happen afterwards when we try to run the program, even in typed Racket, depends on the choice of the mechanism of enforcement we have made. Okay? And there are different answers on what should happen next. And the reason that there are the different answers is that actually our program, there is a problem with our program. When we created this interface and we said that the results needs to be a list of hash tables, we were not that careful. We basically looked at this function, made our assumptions, and we didn't pay attention actually to this little comment for the helper function that says that actually this one does not return a hash table, but returns an association list. Okay? So one answer about what should happen dynamically, which is the original answer about how we enforce types in gradual typing, it's what we call the natural semantics. Okay? So this natural semantics, what they do every time there is a value flowing from typed code to untyped or from untyped to typed, they go and wrap that value. Okay? Usually, if it's a function, it creates a proxy function, and that proxy function intercepts arguments and results, checks that they are of the right kind, and then does the actual computation. This is the original implementation of gradual typing enforcement in typed Racket, actually. And if we want to see what's going to happen, basically, the typed Racket compiler is going to basically export this guy wrapped in a contract that basically enforces that type. So when we go inside our main file, our main module, and we try to call JSON pack, the contract will notice that the result is not a list of hash tables, and it's going to signal a dynamic violation of the type, and it's actually going to give us some help. It's going to give us a message that we call blame that points to the source of the problem. In this case, it has detected an inconsistency between the interface that we wrote and the actual implementation of the untyped library. OK, great. This is very helpful. Now we know what the problem is. We can go fix it. Except that this kind of gradual typing that naturally permits, that's called sound gradual typing, if you Google it, you get really bad news. OK, half of it is about death. OK, and attempts to revive it. OK, so, and there's a reason for that, right? We expect, as we're adding dynamic checks in our program, that things will start slowing down, OK? We also expect that if we add enough of those, maybe the runtime of the language will be able to take advantage of this extra typing information and do some optimizations, OK? The reality is that the slowdowns are so bad that sometimes you cannot use your program. And to make things even worse, how we can avoid these particular configurations, as we tell them of the as we call them, of the program, that do not exhibit these pathological slowdowns, is an open problem. Okay, there are a lot of options, a lot of things that we can do, a lot of different places we can go and add types, and knowing exactly where to invest our effort, we don't have any good guidance from tools or the language. Yes. It's you can. We will get to that later on. There is a benchmark shoot, the gradual typing benchmark shoot, and there is a paper called. Actually, I have it here. The eSound gradual typing dead paper that shows with very specific programs how things go really bad, really fast. Okay. Usually, it has to do with tight loops between an untyped and the typed module. What's happening in that case is that you go back and forth, accumulating more and more contracts, making the program more slow. There is some follow-up work by Robbie Findler and Dan Felty, one of his students, and Ben Greenman, where they show that you can collapse some of those, but it's not the general case. Okay? So, cool. Where were we? Here. So, in the face of this catastrophe of slowdowns, industry, the practitioners, decided to follow a completely different route. And they have what they call the erasure semantics. And what is the erasure semantics? Erasure semantics have other names, by the way. They are type hints, pluggable type systems, Gilad Bracha's from Newspeak from 2004, type hints that exist even before that for Python. And it's actually the semantics that the most famous example of gradual typing in the world right now, the most widely used, uses TypeScript. Okay? So what happens with the erasure semantics? We just forget the types. And TypeScript becomes JavaScript. Okay? And of course, we have no penalty. Okay? Cool. But let's see what this means in the case that we have actually a problem. Okay? When we wrote our utilities code, we assumed that we're going to be given hashes. But instead, we were given association lists. So when we actually try to get the hash out, we get an error. Okay? It's an error that shows up deep inside our program. It has nothing to do with where the error was. And the only information that we get together with this error is basically a stack trace that says that this error, this dynamic error, happened inside this call of this function. Okay? We have to go and connect it actually with the source, which was the mistake in the interface. Cool. So, of course, academics didn't like that, so they tried to make a compromise between the expensiveness of the natural semantics and the everything goes situation of the erasure semantics. And there are many examples, but the one that we will consider today is the one called transient semantics. Okay? That was first implemented as part of reticulated Python, but actually now typed racket thanks to Ben Greenman has also a transient backend. And what happens with the transient semantics is that we are not going to use proxies to protect values that go from one typed module to an untyped one and back and forth. Instead, we are going to rewrite our typed modules. And we're going to rewrite them in a way so that at every place where a problem may show up because of a mismatch, because we don't have something of the appropriate type, we have checks. So we are going to check that the argument comes from the appropriate constructor. In this case, that is a list. When we get stuff out of the list, we're going to check that they're hashes because we're expecting them to be hashes. When we get stuff out of the hashes, we're going to check that they're integers. Just like, so with a bunch of little diffused first order checks inside the program, we are trying to simulate the checks that the proxy will do. Okay? And one of these checks in this particular situation is going to detect that actually we're not dealing with hashes, and it's going to give us a nice blame message, like before, in this particular case saying that there is this value that is coming from client, the main file that we have, does not match what this guy expects here according to its type. Okay? Again, notice that this blame information is a little bit different than what natural gave us. Natural, because it has these wrappers, it's able to connect it with the interface. Okay? So the summary of what I want to say is that basically I showed you a setup where we have a single syntax, a single type system, the type system of typed racket, which by the way, it's very close to the type system of TypeScript. Okay? But we have 3 different semantics and 3 error reporting mechanisms. So now that we have eliminated a bunch of variables about the setup of gradual typing mechanisms, we can go and refine our questions and our question about gradual typing and debugging. And basically, we can say which combination of semantics and errors helps us with debugging. Okay? So I'm closing the parenthesis, going back to the rational programmer. Okay? And now we will work through this pipeline, trying to create this experiment that will help us examine that question. Okay? So we start with the hypothesis. Remember, a hypothesis is valid in this world as long when it defines a strategy. Okay? So we need to develop a strategy as part of this hypothesis. Okay? The goal of the strategy is to take a debugging scenario, and the debugging scenario in this situation is basically some program that combines typed and untyped code and throws a dynamic error, and turn it into another program that does not exhibit a dynamic error, but some error that is some situation that helps us understand where the problem is. Okay? The root of the issue with the debugging scenario is that there is some inconsistency between the typed parts of the code and the untyped. Okay? The types and the implementation. And the reason figuring out where that the reason it's difficult to figure out where that root of the cause is because the code may show up inside untyped code. And untyped code may create values that may flow through the program until they hit a place where typed code tries to use them according to its assumptions and figure out that these assumptions do not hold. Okay? So one way we can start debugging such a program is basically to start adding more types. Because as we add more types, we will turn the inconsistency between types and implementation a problem that can be detected as the type checker works on typed code. Okay? Figuring out what type errors mean is not easy, but at least I claim here today that it's easier than trying to work with dynamic type errors. Okay? So from our perspective, what we're trying to do with our strategy here is we're going to use the error reports that we get together with the dynamic error, either the blame information or the stack trace, and try to ascend through this lattice of configurations on a gradual migration path. And our goal is to finish this search at a configuration that basically we have reduced the dynamic type error into a static one. Okay? In this case, if we've done that, we know exactly where to look for the inconsistency. It's the code that doesn't type check. Okay? Now, we call basically this strategy following the blame trail. And a strategy is successful if it manages to turn the debugging scenario into a one that exhibits the static type error. Okay? So, back to our example. If we consider it if we consider that we are evaluating this example under the transient semantics, what happens is, as I said before, we're going to get a type error, a dynamic type error. Okay? This is going to point to the interface between client main and our utilities little library. So what we go and do is we type check, we add types to the main file, because this is the untyped side of the boundary that was identified by Blaine. We run the program again. We get a new dynamic type error. This time, though, we have different information in the error message. This time, the mistake points to this boundary. So we go, we add types there, and we have reached our goal. Basically, we have detected the source of the error, okay? At least at the module level. Everybody with me about this process? Okay. Let's see how this process fails under the erasure semantics. So what's happening is that we have client summarized that it's typed, okay? And we have this interface that is typed, but really nothing matters about the types when we're talking about how the program runs, okay? So we're going to get our exception that points inside the typed module. So it's not really, we cannot do anything. There is no pointer about where to add more types in our program. So we're literally stuck. Okay? Cool. So now, through these steps, we have defined successfully our hypothesis. We say that if you give me two mechanisms, A and B, if I try A and B on the same pool of scenarios, and one of them is more successful than the other, then A offers more debugging facilities. Okay? Okay, so we've done that part. Let's go and try to target the middle parts of the pipeline, which is actually pretty challenging here. Why? First, for the strategy, the steps of adding types require human creativity, right? There is, as I said before, the problem of migrating code from untyped to typed, it's still open. We have some solutions that work with small programs, but not programs of any realistic size. Okay? The same is true about how we're going to construct a population. The instinctive thing to do here is to basically say, we are going to try and source programs from somewhere, I don't know, from GitHub. We're going to mine these programs. But when it comes to type errors, most of those do not survive testing. So they do not make it into public repositories. So we have to do something else. Okay? So I'm going to show you how we can deal with these two problems together at the same time. And in particular, we will start with the creation of our scenarios. Yes?
Quick one. There's also, I could also think about different quality of types that I might be adding to these modules. That's another axis.
That's another axis why it makes very hard to actually add types, where the human creativity comes in.
Should I be expecting some that we're going to be following a most specific type path for each module?
You will see in a bit.
Okay.
Okay, but that's an excellent observation. There are multiple types that you can add to a particular module, and this creates another dimension of why actually building an algorithmic strategy is tricky. Okay? Okay, so we will start with the problem of creating different scenarios first, because the way we will structure the solution to that problem is going to also help us turn the strategy into a procedure. Okay? So the idea we had is that instead of trying to find programs that already have problems, we can start with a collection of programs that have no problems, and then somehow turn them into many, many programs that have one problem that we know where it is. Okay? Lucky for us, there is a diverse collection of Racket programs, the GTP programs, that are written from different people, from different purposes, for different purposes. They have different numbers of modules and so on. So along a number of metrics, you can say that it's a pretty interesting set of Racket programs. And then we hope to turn those into a bunch of interesting debugging scenarios. So how we're going to do that? We're going to go back in time and look at mutation testing. Okay? So this is actually the first paper that introduced mutation testing does not exist. Everybody references it. We have tried to find it, but we cannot find it. It's not that. It was an undergrad, it was DeMillo's undergrad tech report. Okay, but it doesn't exist. We've searched. Okay, but then they published the paper, and what they describe in this paper is that basically what you can do is you can go to a program and change it slightly in one place, turn a plus to a minus. Okay, small syntactic changes. They call these syntactic changes mutations. They call the means to introduce mutations the mutation operators. And these are basically, you know, rewriting steps, very simple rewriting steps. The reason they develop mutation is to evaluate testing suits. So what you do is you have your testing suite, you get your program, you mutate your program, you get thousands of mutants, as they called. If your testing suite is good, it must kill all the mutants. Okay? As long as they are non-equivalent semantically to the original program. Okay? When they do mutation, they care a lot about introducing little syntactic differences that cause significant behavioral differences, deep bugs. This is not the setting that we are in, okay? Because we want to introduce type-level mistakes, okay? Like this one, for instance, where somewhere inside the implementation, this function is returning an association list, and instead, we have an annotation that says that the function returns a hash, okay? So there are two ways we can actually go and do that, okay? The first way is we can say, okay, the annotation is correct, completely ignore this comment, the comment is correct. The original program, the correct program, had a hash here, okay? So if we want to turn this program into a buggy one, we can go and replace the hash with a cons. Okay? This is what we call a type-level code mutation. It's type-level because it can be detected by the gradual type system or from the type checker if the module is typed. Okay? There's an alternative. We can say, oh, okay, the original program had association lists everywhere, and this should be the correct type. So if we want to create a discrepancy, what we can go is go and change the type. And this introduces a second type of mutations that we call type interface mutations. Okay? So basically, by working with the grammar of the program and the grammar of types, we get different simple rewriting rules that we can apply to inject bugs into our program. I lied a little bit. The interface mutators need a little bit more work. And I'm going to show you why. Let's say that we did the type interface mutation where basically we turn the association type into hash. The client that ends up transitively using this code, if we started with a correct program, does not care that we actually have changed the type. It has an association operation there. So the mistake is never going to show up unless if we have types all over the place. What we need to do to make the mistake manifest at runtime is that we also need to go and update the client. And this is a very big problem, of course, because you have to chase down all uses of this data wherever it flows in the program and try to modify, do all the mutations at the right place. So we took a leaf out of the gradual type book, and what we did instead, we modified the values, not the places where they are used. We created adapters around them so that they flow where they have to go, and when they are used, then they blow up. Okay? Okay, so we apply our mutators to the GTP benchmarks. We get millions of scenarios. We have to ask, are they any good? We need to make sure that these mutators introduce type mistakes in a way that covers a wide range of type mistakes that looks like something that people do. Okay? We need to get different representation of equal representation of all the programs that we had. We don't want the mutators to be dominated by a single program. Okay? So at the end, if we want to argue that we have an adequate population, we need to go and analyze those mutants empirically again, look at them, perform some statistical analysis to make sure that we get interesting, non-trivial debugging scenarios of sufficient diversity. Okay, we were lucky in this particular case, but this is also, and actually, we confirmed that we can get more than 1 million interesting scenarios at the end that are basically interesting. Okay, but in general, this is a step that needs a little bit of care when someone is working with the rational programmer method. Okay, because the results that we get at the end and the conclusions that we draw are as good as the population that we work with. Okay, cool. So now that we have our population down, we can go and talk about the strategy. So in order to turn the strategy into a procedure, we need to do two things. Starting from a debugging scenario, we have to decide where to go next, and we have to decide what types to add. Okay, and we already talked about how difficult the type situation is. It turns out from the two, actually, the types is the most difficult. The error reporting messages that we get back help us determine where to look next. We can algorithmically look at blame messages, decide which component they ask us to go and modify. We can do the same thing with stack traces. Let's say pick the top frame or the bottom frame or one of those, and then isolate a component from that information that is the next that we need to add types. Okay? Lucky for us, the way we construct populations, it's as easy to add types to the programs. Why? Because the GTP programs come actually with types for all their components. Every component has two versions, a typed and an untyped. And those types are written by humans, okay? And we know that they are correct with respect to the implementation. So what we have to do as we go up this migratory lattice is basically we have to go and swap the component we identified from an untyped version and bring in its typed version. Okay? Make sense? Cool. Okay, so now we are ready to simulate the rational programmer finally. We need to do a little bit of sampling. We have way too many mutants. We ended up sampling with some reasonable way so that we get preserve the diversity of the whole population. We ended up going with 100K debugging scenarios, a good number, okay? About 70 for code bugs and 30 for interface bugs. Okay? I want to say a little bit more because it's not what I have hidden a detail here. We don't have a single rational programmer. We actually have 3 variants, okay? Because we have 3 different semantics here that we are dealing with. And in fact, we don't have 3, we have 4, okay? Because blame in transient blames potentially multiple components. So in order to isolate the error information that we're going to follow one of those, okay? So we have 2 different ways. We either pick the oldest one, which is akin to saying we're trying to go towards the earliest occurrence of the manifestation of the bug, or the latest one, which is basically we are treating the blame information the same way we will treat a stack. Okay? And there is another issue that adds a little bit more complexity. These 3 now rational programmers mix 2 different things together. They do both checking that Erasure doesn't do, and they have also an error reporting mechanism. So maybe, since we're doing this experiment to understand and analyze how these mechanisms help programmers debug, maybe we should separate their effects. Okay? Lucky for us, we can easily do it in the rational programmer framework because we can create more variants of the rational programmer. So in addition to those that we have here, we created another 2. Those are just like the natural and transient semantics, but they do not follow blame. They ignore blame, and they just follow the stack trace from the exception that you get from the dynamic checks that those semantics perform. Okay? Which means that any difference in terms of data and validity of the hypothesis we're going to see about these guys and these guys up here will tell us something about how useful blame itself is for its mechanism. Okay? So they act as baselines for blame. Okay? Okay? So now with everything in hand, we can go run a massive experiment. I think it runs for at least 2 weeks on our to run everything. on our big cluster that we have at Northwestern. And after that, we collect a bunch of data and we analyze it, okay? So I'm gonna show you a little bit of the data that we've seen. Lucas talked on Thursday a little bit more extensively about that. I want to show you data that confirms something we were suspecting and data that confirms, that revealed something that we didn't expect, okay? So about the thing we were suspecting, we were expecting that since natural uses properties that connect the location, the types with the place where the typed values are used and vice versa, natural will outperform every other semantics, okay? And this is what this shows. Basically, it's a head-to-head comparison between natural and every other rational programmer we have. Here on the x-axis, we have the various versions of the rational programmer. This is green, meaning that basically for 15% of the scenarios, natural outperforms the natural exceptions. There is no red because there is no scenario where natural exceptions outperforms natural, okay? So you see green across the board. You can see that the results are a little bit more moderate when we are dealing with code bugs, okay? The maximum difference, for instance, between the difference between erasure and natural is about 11%, and down with transient it goes to 4%. The results are much more impressive when we are looking to interface bugs, where the difference with erasure goes to above 20%, okay? Now the surprising part. I talked about these baselines for blame. If we try to see how those rational programmers compare to every other mode, it's abysmal. They do really, really bad. So which says that basically if you take from gradual typing blame, and all these checks actually that we have are there just for debugging, if you take blame, then basically we negate the benefits of sound gradual typing. Okay? So, what we learned? Two things. Natural blame is the most useful in terms of debugging. Checking without blame is subpar. I want to say that this second point is also interesting for another reason. If you open any theoretical paper about gradual typing, most of the times blame is excluded. Okay? There is a third point that I want to make, and this has to do with how bad is the performance of sound gradual typing. We tried to look not only at how useful these semantics are to help you debug bugs, but also if they detect the problems. Two different things. Do they raise an error, or is the information useful so that we can go and find the error? And then when we collected that data from our experiment, we saw that the erasure, the one that doesn't check anything, the cheapest one, detects approximately the same number of bugs as the other ones that do the expensive checks. Okay? Of course, I have to say that this is an experiment, so we have to be clear that there are threats to validity. Okay? This is all done in the context of typed racket. If you go to a language with a different runtime, the experiment cannot generalize there. It needs to be repeated. It's about the particular type system. It's about the particular population of programs. So with a little bit of salt in what I say, I think that we have some evidence that says that a language designer who wants to add a gradual type system to their language, maybe they should consider erasure for production, okay? And then use blame and natural semantics as a debugging mechanism, as an alternative semantics to try to get more information and work offline with their program. Okay? Now, I want to take in the last few minutes a step back and talk a little bit about the big picture besides the rational programmer, and in particular, why we call this rational. Okay? So, the reason we call it the introduction of rationality in science goes way, way back. Okay? One notable point is John Stuart Mill and his idea that later was called Homo economicus. Okay? He didn't name that. Studies of Mill's work basically called it the Homo economicus. The idea there is that if you want to understand how humans behave, you should create a rational abstraction. Rational means they try to maximize their benefit, okay, in some situation. And put them in a setting where if you try to understand how different economic agents interact, all you have to do is to try to figure out how they can reach a balance between their interests in that setting, okay? This idea has seen many interpretations, many uses. It has been abused heavily. It has also influenced significantly the study of game theory and CS economics to get combined with Bayesian statistics, okay? The one that is more closer to the rational programmer is some ideas by Herbert Simon about bounded rationality, where basically it's a criticism to the original ideas of rationality by Stuart Mill, where Simon basically said that, you know, humans do not have, they're not omnipotent beings. They cannot consider, you know, optimal solutions at any point. Instead, they're trying to find a solution that satisfies. And he introduced that work, their goals. So it may not be the optimal choice at the current point, but it's good enough. And exactly that's what we try to reproduce with the rational programmer. Of course, all of this work has mathematical underpinnings and statistics and decision theory and so on. We don't do the same. The connection is at the metaphor level at this point, okay? But the real reason I mention all this is because I want to say that we shouldn't confuse the rational programmer with a real programmer. It's a strategic simplification so that we can do an experiment, okay? Exactly what the rational programmer is, it's a device for figuring out connections between the design and the semantics of the programming language and the benefits that it can offer in a particular context. It does not mean that if we take humans out of the street and ask them to repeat this process that they will be able to repeat it or that they will choose to repeat it. The questions that we ask with the rational programmer are questions of what we defined as PL pragmatics. They are not questions of usability or human-computer interaction. Okay? The interesting thing, though, is that now we have some way to connect actually the semantics of the programming languages with bigger picture uses of the same features of the programming language and do apples-to-apples comparisons. So far what we've done with it, I talked today about the middle bullet. Before that, Lucas, my student, had also worked out how we can debug with contracts logical mistakes. And we have an upcoming paper at UPSLA where we look how profilers can help us navigate type what profiling strategies we can use to figure out which place to go next in the migration lattice to avoid slowdowns. Okay? And I'm going to conclude here and open the floor to questions. I just want to say that it's not just me. Besides Lucas, Matthias, and Ben that I have already mentioned, Alexis King, Robbie Findler, and Kaspar Popova have been part of this adventure of the rational programmer. Thank you.
So open to questions.
I have a question about heuristics. Have you been able to come up with some kinds of heuristics that help you sort of monotonically increase or make your way towards the goal through that lattice?
That's an excellent question. So actually, we looked in this. We looked exactly into this topic with our first paper, not for gradual types, but we looked how contracts, falling blame for contracts, whether it gets you closer to the goal. Okay, and it's very surprising. In most scenarios, it does. The strategy of following the blame, but there is a very weird corner case in the implementation of Racket's contract system that violates this monotonicity. And here is what's happening. So it has to do with the interaction between state, hidden state that the runtime uses, and the contract system. So what's happening is when you hash a value, there is some hidden state that generates the keys, okay? And then iteration over hashes depends on those keys, which are, this counter. So if you write a contract, like the ones that we wrote, that were extremely precise, that were actually adding values to sets, which are implemented underneath with hashes, in order to check set properties, you change the value of the counter. So just adding the contract interferes with the actual behavior of the program, causing different contracts to fire up depending on what contracts you have in the program. Which means you may add a contract, expect that you will get closer, but all of a sudden a different error shows up that gets you further away. Okay? We haven't found something similar with the gradual typing, and the reason for that is that it's very hard to instrument Racket's runtime in order with proxies, the way we try to do it, to get information. In fact, it was Alexis, when she was at Northwestern, basically worked on building for us and the infrastructure that we needed for that experiment. Yeah.
Thank you. Wonderful talk. We started this discussion looking at a language with the same syntax, the same language, same syntax, and 3 different semantics. I'm interested in investigating teaching language progressions and afraid of doing user studies. So it seems like the rational programmer might also be applicable to different related languages.
Exactly.
That have chained on. Okay, cool.
I believe, I haven't tried it, so I cannot say, but I believe that it's doable.
Cool.
Okay? I don't want to say something now, that later on.
I won't hold you to it.
Yes. Yeah. Okay.
I'll try to ask a question. So it seems like the idea of blame is like a single point. And oftentimes it seems when you really have real problems, it's not 1 point, but it might be 2 or 3 or a pathway. Is that a valid idea? And I'm thinking about, oftentimes programmers will talk about a smell. This smells funny. I'm wondering if there's something there that, to give the idea that there are areas that are more suspicious than others.
Yeah, so you're absolutely right. Blame points to a single place in the code. And in fact, as this experiment showed with data, we knew that in a theoretical and anecdotal level before, but now we have data. Blame does not point you directly to where the problem is. You may have to do a transformation, chase blame a little bit, chase it again and again and again until you get to the blame. So there is a question whether we could have provided that information from the beginning and give basically a trail through the program of changes, or identify the most problematic piece of code and so on. Yeah, you are absolutely right. We haven't done that. I don't have any idea how to do it. But yes, blame is not the location of an error. Yeah.
So if you wanted to move to sign to satisficing and incorporate that into your framework, do you have an idea how you would do that?
We already implement is a little bit very precise, but we are already inspired by bounded rationality. I think the idea of the optimal rational programmer is unrealistic, because we don't, if I see an error, I'll go the optimal choice is to go as close to the error as I can, right? So that's why the rational programmers we construct are already bounded, in the sense that they are trying to go to maximize what they can do with the information they are given, without looking for tools outside the feature that they are working. For instance, we don't look at some extra debugging tool that we may have and so on. We just look at the type system, and we're trying to make a choice that may not be the best, but at the moment, with the information we have, we hope that, and the experiment confirms, it gets us towards a solution. Yeah.
So I don't know if you've seen, you have thought about this idea before, but would this work, for example, to verify a communication protocol between components that are distributed?
Yes. I don't know how to do it. I expect that the undertaking of constructing an infrastructure where we can perform this kind of... So, for instance, Lucas, my student, has spent more than a year on just building the infrastructure for running the experiment. And he had to do it twice. We don't know yet how to generalize the infrastructure that we have. He had to do it twice for the 2 ICFP papers and once more. So basically, he spent his whole PhD on building infrastructure in order to do the measurements, okay? So I don't know how hard and how time consuming and how, difficult it is to construct something like that for a distributed system. And there is also, I don't know how, it's an open question, how we can actually create scenario. Because mutation was something that was around. I'm not sure if there is something similar when it gets to basically trying to break down different, to do things to violate protocols and then see how easy it is to find them.
Yeah, so I've had this discussion with Matthias before.
Okay.
So it's really I'll give you a very specific context, right? So I teach CS1 students how to do distributed programming. And of course, some of the nastiest bugs are the ones where the communication protocol is violated.
Yes.
Right? And
yes.
so the question is now, how do we pin that down, right?
Yes.
So it would be a wonderful case study, right? If you ever come around to figuring this out.
Yeah. By the way, it's some work by Cameron Moy and Matthias on something called trace contracts, which are contracts for basically observing sequences of interactions and can be to observe protocols. And it comes with blame. And of course, it's an open question how useful that blame is.
Yep.
I want to say something that I forgot. I said that the rational programmer is not about humans directly, but we learn strategies, okay, that work. And we have hard evidence that they work in certain cases. So we can use this knowledge to explain the benefits to students and then teach them the strategies. Okay, so for instance, my PL course at Northwestern, the last week is spent on what we call pragmatics, where basically the students come in the class and they basically perform rational programmer-like exercises. Okay? Yeah, sorry. Thank you.
Thank you.
C'est Marc.
Will you say something?
Hey, test. 1, 1, 2, 1, 2, test. Yeah, everything's good? Is it loud enough?
Oh yeah, it's good.
Okay, perfect.
And would you like have 5 minutes of Q&A at the end? Or
Yeah, 5 minutes
Okay.
of questions,
we'll
yeah.
show you this one.
Okay, perfect, yeah. That's good.
I guess we just need to wait for the session to finish.
Is there a way to follow that live?
Yes, it's on YouTube. If you go on YouTube and you search ICFP 2023 Olympic, Olympic is the name of this room, and there's a live stream.
Okay, perfect.
Let's see. All right. I think we're back from lunch, everyone. Welcome to the third session of the day. Leonard is going to start by telling us about the latest and greatest in an R4 RS compliant REPL in 7K.
Hi, thanks for having me. My name is Leonard Ernst O'Leary, and I'm going to present an R4AS compliant REPL in 7 kilobyte. You may have noticed that in the title it's 8 kilobytes, but it already shrank a little bit. So, yeah. This work has been made possible because of Mathis, who is right now in the room, and Marc Filet, who is probably watching right now. So hi Marc. So yeah, let's jump right into it. So, sorry. Okay. What is R4AS? So I'll start slowly because maybe some people don't know what R4AS is. R4AS is the 5th scheme standard, and it's what we consider as the first modern scheme. It was released in 1991, and so it's been a while. And just to refresh a little bit your memory, here is everything what is contained in it. So it has 164 essential procedures, 18 essential syntaxes, has file I/O. It has rest parameters, quasi-quote, unquote splicing, call CC, load, eval. So it has a lot of features. It doesn't have essential macros right now in the eval feature, but still it's a big it's a big standard, by big relatively to scheme. And now let's just do a little experiment. How small is 7 kilobytes? So we are used to manipulate like gigabytes right now, so it's good to remember that what 7 kilobytes is. And if we take the first 2 pages of our paper as text, this is 7 kilobytes. So our goal today is to fit the whole R4S standard inside 2 pages of our paper. So we'll talk a little bit about the technologies we used for doing this. So this talk is going to be split into 2 main parts. First one is going to talk about what Ribbit is. Ribbit is the system that we use to compress the REPL. So in short version, it's a scheme implementation based on a virtual machine that is compact, extensible, and portable. The second part of the talk is going to be how we changed Ribbit so that it can fit a REPL in 7 kilobytes. So a little bit about the origins of Ribbit. Ribbit was motivated by a fascinating project called Sector Lisp, which was able to fit a Lisp implementation with GC in 512 bytes. While a nice experiment, it's more a curiosity than an actual practical because it's not extensible or portable. So we wanted to take a different approach to reducing code like this, and this is what we present as Ribbit. So Ribbit is portable. We define portability as the effort required by a programmer to get the VM working in a different environment. Okay? And our approach is a bit different. So we implement by hand new virtual machines. And because the virtual machine is quite small, this takes about 2 to 3 days to do. So adding a new host is 2 or 3 days of work about that. And here are some implementation that we already have in Ribbit. So there's one in JavaScript, in assembly, in C, and there's more of them here below. As you can see, they all have a similar structure. We all have the RVM code, which is kind of a bytecode. It's not really a bytecode. I'll go more over on exactly what it is. And here we just have a while loop to represent the interpretation of this kind of bytecode. So as we can see, we have a couple hosts right there. Ribbit is extensible. So we added a new construct that we call define primitive that lets the user in Scheme write directly new primitives inside its Scheme code. So as we can see here, if we want to define the square primitive that will just square a number, you can use define primitive here to define it in Python and in C. And this can serve as a simple FFI. Note also that you could use define primitive to call, for example, libraries in Python or things like that to interface with them. Ribbit is compact. You may know about our previous work that was able to fit a VM compiler and REPL in 4K. This, while impressive, it's a bit far from R4AS. It didn't support file I/O. It was a subset of R4AS. And it was 4K in the JavaScript host with the min library, which has less features. To compare it with what we have right now, this is what was in the previous REPL, and this is what we have now in the new REPL. So we see that there's a lot more procedures supported. And the whole R4AS standard is supported in the new version. Now I'll go a little bit about things that Ribbit do to compress the code. So one thing Ribbit do to compress the code is a liveness analysis. So it does a liveness analysis inside the source code by, for example, removing the read procedure if we only display. But it also does it inside the RVM. So if we never use a primitive, for example, putCar here to print, it should be getCar. So if you, if we never use a primitive, it is removed from the RVM. So this allows us to really tailor the RVM to what we really want. The RVM is the Ribbit virtual machine. So yeah. Let's have a little bit of a closer look on how exactly Ribbit works. So we start with our program that we want to compile. And we start with an RVM implementation here. So we could choose any implementation that we have. There's a lot to choose from. Here we chose the JavaScript one just as an example. And we feed both of them inside the Ribbit AOT compiler. So the scheme is going to be parsed, expanded. There's going to be liveness analysis. And at the end, we are going to generate what we call the RVM code graph. So it's a graph that contains the values as well as the whole code. I'll go more over what is contained inside this graph. And then we serialize this graph into the Ribbit intermediate representation that we call the ribbon. So the ribbon is then going to be embedded inside our program. Our program. So our program is going to be embedding the intermediate representation. I told you earlier that it isn't really a bytecode, and the reason is because while doing this, we generate the whole RVM and we tailor it, we change it. So the compiler is going to maybe remove primitives or reorder them or remove features inside the RVM. So the bytecode here, you cannot take it and put it in another RVM. It's not going to work. You have to pass through the compiler for it to work. But this gives the compiler more power over what is included inside the final executable. Now we'll do a little overview of the code graph that we saw earlier. So in Ribbit, everything are ribs. Ribs are a three-field vector that can contain either instructions or values. Here on the left, you have a few examples of values that are contained with ribs. So the pair, for example, is a three-field vector where the first field is the car, the second field is the coder, and the third one is a tag to say that it's a pair. And ribs can be nested. So inside ribs, you can reference other ribs or numbers. And the whole program is represented this way. For the stack machine, it's a pretty standard stack machine with 5 instructions that pretty much resemble the 5 instructions in Scheme. And we also have a small set of 18 primitive procedures that are used either inside the standard library or used by the compiler. I didn't include the I/O primitives because we changed them with the R4S library, and we used our define primitive to do so. But if you want to do file I/O, there's a little bit of primitive to add, but it's not that much. Now we'll go over a little execution example. I won't say exactly how the program executes here. The only thing I want you to remember is everything is ribs in Ribbit. So you see here the program, the instructions get, const, call that you see in red here. These are instructions in Ribbit, and these are nested ribs. Yeah, so they represent the whole program. We also see that our stack is represented as ribs. Here, yeah, I didn't say it, but this is the exponential function here that has been compiled to the our RVM code graph. So everything are ribs here. And the symbols as well are, for example, ribs that point to other information. Now let's look how a typical RVM looks like. So here we have the RVM in Python. So first we have here a section that embeds the ribbon. So here it's the section where we input the ribbon. We have also here a section that decodes the ribbon. So it's going to transform this ribbon into the code graph. We have here a section that interprets the code graph. So it's running on the ribs and doing the different operations. And finally, here we have a table of primitive that is going to be used by the RVM code graph executor or the runtime to know which primitive is being called. So now we're going to go over a little bit about how do we serialize the program into the ribbon. Yeah. So first of all, the ribbon is made out of 2 main parts. There is first the symbol table and the decoding instructions. The symbol table is constructed from left to right. This is because it's simpler to decode it this way. In Scheme, often we start with nil and then construct our list this way. Symbols here are in reverse. So for example, if you look at the first one, it reads Izolk or something like that. If you reverse it, it's close. So it's for creating a closure. And we have, also, the symbol table is going to be represented as ribs in Ribbit. So here we have a link list. So the first one, we have the list of symbol with the tag that starts with 0. And on each of them, we have, it links to a symbol in the symbol table. So for example, the first one is the rib, and we have a few anonymous symbols. or unturned symbols that we just need to call. So there is here is the representation of the symbol as as ribs. Yeah. So. And the values of the global variables are stored directly inside the symbols. Now we're going to go over the decoding instructions. So to do the decoding of the ribbon, we use another stack machine that has its own instructions. So these are pretty classic instructions. We have push, that just pushes a new value on the stack. We have link, that takes the top of stack and links it so by the third field of a rib. And we have merge instructions that take the two value on top of stack and create one rib with them. For example, the merge instruction is used to create ifs because both flows are going to be on the stack, and we're going to take them to put them inside the if. Here I have a little animation about how this is all going on under the hood. We have the stack here. On the right, we have ranges that are associated with each instructions. So for example, the instruction push 0 here has a range 0 to 19. And when we are decoding, we take each of these instructions and running it. So for example, the first one is a push instruction. So we add a new rib onto the stack. And this rib links to a value on the symbol table. And while doing this process, so for example, here we have another instruction that creates another rib. And here we have another instruction, again, linking the rib. And note here that the instruction is what we call long. Some instructions can be encoded on multiple bytes. This lets this is because sometimes we need to encode the argument on more values. So at the end, we are going to end up with one rib containing the whole program, like that. And then the second phase is going to kick in, and we're going to execute this code. So now we've understood what ribbit is. Now we're going to see how we enhanced it to fit a REPL inside 7 kilobytes. So the journey to 7 kilobytes. Here is a picture of the board in our lab that we had. And at first, as you can see, we wanted to call the paper R4KRS because we didn't achieve the 4K, but we still achieved 7K, which is pretty good. And so we used a lot of techniques to shrink it down. For the rest of the presentation, I'm going to use a scale here to show you to show you how much kilobytes we saved by each technique. So as you can see by the photo here, we started at 18K. So the first thing we did is writing R4AS with style. So we rewrote a little bit the library because our first way of writing it was not optimal for space. So for example, using higher order functions or not boxing characters when dealing with I/O. So these are simple techniques of transforming the code a little bit. We didn't do too much of it, just a little bit. The second part that we did is we enhanced the encoding. So the encoding that I showed you had some flaws. For example, it was only using 92 codes. So the string that you saw is the ribbon. Is the ribbon it's the ribbon, and we can use 256 codes when we compile. When we use compiled hosts. For example, on C and an assembly. This is because it doesn't take more space to represent this data inside those compiled hosts. So using the whole code really improved the compressing rate. The other thing is the decoding instruction that I showed you cannot represent a directed graph. directed acyclic graph. Can only represent a tree. So this has some issues, and we'll go more over and how we fixed it. And the encoding is not specialized to the source code. So we have now a new encoding that can be specialized to the source code. So now I'm going to talk about the share instruction. This is the instruction that allows us to represent the code graph as a directed acyclic graph. As we can see here, we added a new instruction. So before the share instructions, we couldn't express a tree-like structure. We could only express a tree-like structure like this. This is a simple positive function that turns a number into a positive value. And we can see that the continuation of the if here, it has to travel two different paths. Either it is true and we do the multiplication, or it is false and we do the multiplication. So if we cannot represent a DAG, we have to encode the graph with the two flows that you see here beneath. With the share instruction, we can take a certain value on the stack and push it again. So we can represent the graph as a DAG as shown here. The second thing we did to improve the encoding is encoding specialization. Inside all RVM hosts, we have special annotations that you can see here. These annotations, I won't go over what they do, but they give additional information to the compiler to do some modification of the RVM. Remember that we generate a whole RVM, so we can modify it while we compile to the final host. And here, this means that the compiler can have an algorithm to decide the best ranges to assign each encoding instructions. And here is the output of the compiler. And you can see that it assigned a certain range to each instructions. And because of the annotation that we have here, we are able to replace it after compilation to have this vector embedded this way. This lets us really fine-tune the RVM to the source program to minimize it as much as possible. And the algorithm inside the RVM, what it really tries to do is to minimize the use of long instructions. It will give better ranges to instructions that are used a lot with small indices. This way, it can really encode the fewer long instructions and compress the code as much as possible. The third technique we used is compression. So we used a classic algorithm called LZSS. And it's a compression algorithm based on back pointers. So instead of representing similar strings by just repeating them, we represent them as back pointers. So a certain offset back and a certain length. Our main challenge was to encode back pointer, was the way we encode back pointers. So here is the way we did it. We reserved a certain range of the 256 code for compression. And on this range, we took the second byte and combined it into one number. Then the compiler decides at compile time what would be the maximum length possible for a back pointer. And this information is injected inside the RVM. This way, it lets us decode the back pointers and by doing a simple division or modulo operation. So this is like the high overview of how we decode, how we compress the code. And in a similar way, we embed the information like this inside the compiler. So now we can talk about results. We explained pretty much how the system works. And we were able to, a little animation here, I was really proud of it. We were able to define a REPL that is R4S compliant inside 6.5K. Here it's written 666, but if you convert it into kilobytes, it's going to give you 6.5. As you can see, I just did a little example here. where I did open an input file, actually an output file, and I write on it because the IO primitive was something that was a little bit tricky to implement. So I was kind of proud to just have an executable that's 6.5K and that can write to a file. It's pretty cool. And you may ask yourself, is it fast? Because we did a lot of things, so is it still decently fast? And it's still decent. We compared it to GSI, which is Gambit Scheme Interpreter. And as you can see, with all the optimization, which you can see more in the paper, for example, PNA is one technique we use to make it a little bit faster. We can see that it compares pretty well to GSI. If we add type checking, we see that it's a bit slower, but it's not that much. The only thing that is really slower is here the deriv benchmark. And this is because it uses a lot of higher order function with apply, for example. So we still have to look into that because why it's a bit slower. But we have a good idea of how to fix it. So future work. We believe that we can fit an R7 RS REPL inside 15 or 30K. So we're going to see if we're able to do this, but this is something we want to work on. So thank you very much for listening, and if you have any questions, I'll be happy.
So I'm sorry if I missed something very basic.
Yeah.
So you have this compiler that compiles your R4RS implementation into Ribbit. That compiler, is it written in Ribbit? Or?
No, it's written in Scheme. Okay. So we had some version that bootstrapped. Mm-hmm. So that means that it works with Ribbit. And there's no inherent difficulty of making it bootstrapping. Right now, it's not bootstrapping, but it's just a question of making it work.
And the R4RS implementation itself, is that a straight-up interpreter, or is it itself, or does it compile to ribbons itself, or how does that work?
This implementation is a library that we wrote in Scheme. That is like.
But when you type in a scheme expression that it then evaluates, does it straight up interpret that expression, or does it itself compile it to a ribbon?
No, it doesn't compile. It's self-contained. It's an interpreter, so it works. Okay. Maybe I can
provide additional information. So basically, we have this library. We have R4RS as a library, which you can include in your code. So basically, there are files which contain all the procedures and all that. For the REPL, we have a small interpreter written in Scheme, which is also in the REPL, which contains less feature than the actual compiler to make it small, have the smallest footprint while staying R4RS compliant in the REPL. So we have like a small interpreter written in Scheme, which can include, which is eval basically. And we also, for the rest of the procedures, they are written directly in Scheme, which can include them. Yeah. If that answers your question.
Hi, thank you. This was really cool. Also, just sort of a confirming question. So when I run the compiler, it produces this encoding decoding schema of the compiled Scheme code, as well as an implementation of a virtual machine in some language?
Exactly, yeah.
Okay.
So, yeah.
Yeah. So I guess two questions are, you mentioned it takes 2 to 3 days to set up?
Yeah, to write a new RVM. Once it's written, you can compile to it pretty easily. Yeah, each RVM is about 200 to 800 lines of code. So it's really a small program to write.
I see. So it takes 2 to 3 days to generate that specific RVM for a given program, or?
No, for a human. So once you have an RVM implementation, you can compile instantly to other hosts. But to have a new host or a new language added to Ribbit, you can write a new RVM, and this takes about 2 to 3 days.
Right,
But
okay.
it's a manual work, like you code it.
Sure. Sorry, I was under the impression that you would generate an RVM specific
No.
to that program. Is that not true?
Yeah, we do generate
Okay,
an RVM
yeah, sorry,
specific to
maybe
that
I'm just
program.
confused. Yeah.
We do generate an
Yeah.
RVM, but that is done by the compiler with annotations inside the RVM that you have written. So there's like two RVMs.
I see,
There's
okay,
the one
so
in,
you're sort
as
of
input with annotations.
Basing off of an existing
Yeah.
one. Yeah.
And there's
okay.
the final one. Yeah.
Got it. That's really, really cool. All right, thank you.
you.
So, if I wanted to make my own RVM, is there a standard by which I can refer to implement my own RVM in, say, RISC-V assembly?
There are a few implementation available on our GitHub that serves as like.
But you don't have like a formal spec of like when like this is the instruction and this is what it does and kind of like any other sort of ISA.
Yeah.
Do you have an ISA for this VM?
We don't have one yet. We are working on it to add more documentation for it. So there's a wiki ongoing. So if you go on it, it's quite small, but it's something we want to do so that people can implement their own RVM.
Yeah, I think that would really like sort of speed up the development of it. So if I wanted to spin one off,
Yeah.
I don't have to like kind of guess or know. I can look at the standard and then verify it myself that yes, this is indeed an official RVM, and then I can, then it's easy for me to compile to it, and then I can run that interpreter for that particular RVM.
Yeah.
Okay.
Yeah.
So first, just thank you for the talk. It was good.
Thank you so much.
Can we go back to the slide where you have your benchmarks?
Yeah.
So just a piece of advice here. Some of these benchmarks go back to Gabriel's original studies. Some of these benchmarks go back to Gabriel's original studies to write benchmark implementations. And so they're not that interesting anymore. For example, FIB and ACK and TAC.
Okay.
Right, well, those comes from the days when we weren't sure how to do recursion efficiently.
Okay.
So I would advise you to maybe look at some more modern applications.
We actually took the benchmark of Gambit. So these,
which is
and
historically
we took
comes from Gabriel.
a subset of them, but yeah, it would be interesting to try to benchmark it on more benchmarks.
And so my question now, have you ever, so these ribbons that you produce, right, are specialized but depending on what is needed by the program?
Yeah, exactly, yeah.
Have you ever thought about doing that using a macro?
Using a macro inside the RVM, you mean?
Yes.
It's our annotation system is a bit like macros, but it's hard to have a system that works well because there's so many host languages. But yeah, it's we have like kind of annotation that can be embedded, and it's scheme code that runs in the background. So
okay,
yeah. Thank you very much.
Any last questions? All right.
Hi, Audrey So, University of Washington. This is super cool and a very fun presentation. I'm just wondering, like, is there a reason why you want to get a very tiny interpreter, or like a specific like use case, or is this just for fun?
I mean, doing it in 7K, it's a fun experiment, but there's actual use cases to this. For example, if we want to have a small JavaScript implementation that runs fast on the web, this could be like a motivation. Also for like embedding systems, or so there's a lot of use cases where having small implementation is useful. Actually doing it in like 4K instead of 7K, this is maybe more than a fun experiment than something. Yeah.
Okay, cool.
Thank you.
Hi, Alexei Radl, Google. So I assume that your generated RVMs depend fairly heavily on facilities from the host language.
Heavily on what? Sorry.
Like you generate a CRVM, it runs on Ubuntu.
Yeah.
It can invoke arbitrary kernel functions from this like hundreds of megabytes of binary garbage. Have you looked into getting all the way down and stripping out the operating system so you can generate a tiny virtual machine image that just executes the program?
We haven't looked into this specifically. We have a x86 implementation, so this is quite like near the machine, but we still have the kernel to take care. So we could maybe try to go even lower. And
I mean, there could
build
really.
OS.
I heard might be various other projects like this, but there could be an interesting direction because, like, one of the user-facing problems in Google Cloud is that it takes forever to spin up a VM because they have to ship a gigabyte-sized image to the VM hypervisor that's going to execute it on Node. If that image can become 1,000 times smaller, that could be very interesting.
Okay, yeah. Thanks for that.
I have a surprise. Oh, let's thank the speaker one more time, please.
Thank you very much.
We have right now time for a surprise talk. Arthur had a quick major announcement.
Hi, yeah, so I'm Arthur Gleckler. I'm the editor of the Scheme Request for Implementation. I actually followed Mike Sperber, who used to be the editor. And I've been asked by the Scheme Steering Committee, which is essentially a group of... Oh, you still have your microphone on. You still have your microphone on.
Oh, sorry.
Yeah, a bit awkward.
Okay, here it is.
Yeah. Yeah. So I won't be that entertaining, but the Scheme Steering Committee is a group of folks who basically are the level above the working groups that are working on R7RS small and now R7RS large. They asked me to make an announcement because earlier today we got a new editor for the, new chair for the working group that's doing R7RS large. So let me just read this. This is actually written. So yeah. So Mark, if you're watching, here I am. The Scheme Language Steering Committee, whose members are Will Klinger, Mark Feely, Chris Hansen, Jonathan Rees, and Olin Shivers, these are all people who've been in the Scheme Standards effort for a very, very long time, would like to make the following announcement. Following the recent letter of resignation of John Cowan as chair of R7RS WG2, Working Group 2, we have accepted John Cowan's resignation with our deep thanks for his exceptional service. His leadership, devotion to the task, and many contributions have been extremely valuable for the evolution of Scheme. We look forward to the continued contribution of his expertise and input as the R7RS process continues. And then the steering committee has appointed Daphne Preston Kendall as the new chair of R7RS WG2. In moving forward, the steering committee intends to have more frequent interactions with WG2 with an overall goal of bringing the Scheme community together and finalizing the R7RS large standard in the not too distant future. And this is again from Mark Feely, who's representing the Scheme Steering Committee. So that's the announcement, just a very quick thing. R7RS continues. So, I'm taking questions. So you ask, does Daphne bring new process to the new direction to it? She has definitely some new ideas. By the way, John Cowan strongly supported her and endorsed her choice, choosing her as the next chair. So she's written about that in her blog post about the whole process before she took over. And I'm sure new things, she'll be writing more to come out. But yeah, they do have some ideas for simplifying. I don't want to speak for her. That's a good point. We should put something on scheme.org. Thank you for the point. As soon as I get anything, I'll put it up. All right. Thank you, Arthur. Yep. Thanks, everybody.
All right, and our last talk of the day is going to be a remote talk. Yu is going to be telling us about designing a language for learning continuations.
Hello everyone, I'm Yu Yotong at Tokyo Tech. In this lightning talk, I will propose a language for learning the concept of continuations. This is something that I plan to create in the next few years, and the purpose of this talk is to get some advice from the Scheme community. Okay, the motivation of this work comes from the recent introduction of continuations into various programming languages. For instance, the latest version of OCaml implements concurrency through effect handlers, which can manipulate one-shot delimited continuations. Haskell recently added support for delimited continuations via control operators, and Scala will be extended with similar features to implement suspensions. What this means is that continuations are becoming something that every programmer should know how to use. However, for many people, continuations are hard to understand at the beginning. This is a quote from a paper by Chris Barker, a linguist who uses continuations to explain natural language phenomena. He says, "The idea of continuations is notoriously hard, and you need to go through a number of examples to understand this concept." This is based on his experience of learning continuations as a non-computer scientist, but even for computer scientists, self-learning continuations can be difficult, as witnessed by the large number of tutorials on continuations that are available on the web. Well, maybe not as many as monad tutorials, but there are a lot. To help learning of continuations, I propose to build a pedagogical language for learning continuations. This is inspired by the Teach Scheme project led by Matthias Verleisen, Robbie Findler, Matthew Flatt, and Shuram Krishnamurthy. In that project, they claimed that a beginner of programming should use a dedicated language so that they can focus on the essential concepts and get appropriate support. Similarly, I believe that a learner of continuations should use a specially designed language for a better learning experience. Now the question is, how should we design a language for learning continuations? I think there are two key requirements. First, the language should be gradual in terms of complexity. And second, the language should be able to visualize continuations. To implement these requirements, we can borrow two things from the Dr. Racket programming environment. These are language levels and the algebraic stepper. Let me first elaborate on language levels. Language levels define a series of languages with increasingly rich features. This helps the programmer focus on new concepts and also helps the compiler produce good error messages. In the context of learning continuations, we would need to consider two dimensions of restrictions: side effects and usage of continuations. The first dimension is necessary because continuations interact with side effects in a non-trivial way. My current plan is to only allow printing at the beginning, then introduce mutation and exceptions. The second dimension is necessary because advanced use of continuations adds complexity to the program behavior. I'm thinking of forcing linear usage first, then enabling multiple calls, and lastly allowing first-class use. Let me next explain the algebraic stepper. An algebraic stepper displays the execution of a program step by step. In our context, a stepper serves as a visualizer of continuations, It shows what continuation is captured and how it is used. I believe that this would be extremely helpful for understanding and debugging programs. When I was learning continuations, I often manually wrote down all reduction steps to figure out what is happening in my program, and that was both tedious and error-prone. With a stepper in hand, we can step through programs just by clicking the previous and next buttons. In addition to implementing these two requirements, we need to make some non-trivial design decisions. These include which control operators to use and whether the language should be typed. In the continuations literature, there exist 4 variations of control operators having the same syntactic structure but slightly different semantics. Shift and reset have the simplest behavior, while control and prompt have the longest history. Shift 0 and reset 0 are close to effect handlers, which are becoming popular, whereas control 0 and prompt 0 are most powerful in that they can easily encode the other 3 variations. I used to be a fan of shift and reset, but nowadays I also like shift 0 and reset 0, and if you ask effect handlers people, most of them will say shift 0 and reset 0 are the best one. Turning our attention to types, there are both untyped and typed implementations of continuations, and typed implementations can further be divided into 2 groups. The 2 groups differ in whether they allow answer type modification, that is, whether the return type of a delimiter can be different from the return type of a continuation. Personally, I think types help us understand what kind of continuations we are manipulating, but I'm not sure if I want answer type modification, because although we get additional expressive power, we may encounter complex error messages. Alright, to summarize, I'm designing a language for learning continuations. I plan to include language levels and an algebraic stepper for better learning experience, but I haven't decided which control operator and type system to adopt. Now, I would like you to share your thoughts about how I should design this language. I'm also interested to hear your experience in learning and teaching continuations. So, please speak up if you are in Seattle or email me if you are watching remotely. Thanks!
All right. Well, I guess you opened the floor for discussion. So, does anybody want to offer suggestions or thoughts?
Hello. Hi. Could you go over the motivation behind making this separate language instead of using another language which supports continuations?
The motivation of designing a language specific for learning continuations?
Yeah, like are the continuations in this language easier to understand than they are in like general languages which have continuations?
So, for instance, in Racket, we have a lot of control operators ready for use, but we don't have support for sufficient support for understanding like what kind of continuation is captured in a particular computation and how it is used, right? For instance, Racket has an algebraic stepper for the teaching language, but it doesn't work if you use control operators. And I think this kind of support is very important for novice learners of continuations.
Thank you.
Hi.
Hi.
Thanks for your talk. This is really exciting. I'm a TA at a university in the US, and it is really hard to teach continuations. I feel like probably 20% of people get it on a good year. So this is a great project, I think, and I am like very interested in this. I don't know much as a student, but from what I've seen as a suggestion, I would probably suggest with going untyped, because I think integration of a type system, at least at the point where we teach students, we teach them, the basis of functional languages like Scheme, before we teach them these full, statically typed languages like ML, which introduce a whole other set of constraints and issues. And I think part of what can be cool with continuations is seeing the threat of execution at runtime, including when you make a mistake and it's badly typed, and at some point you call a continuation with mismatched types and everything explodes. I think that's easier than having the type checker just tell you, because that can be kind of, I guess, too dense and arcane. But having it all sort of add up at runtime and letting things run out, especially with stepping, can sort of help see, oh, well, I changed this and this is wrong, but now I changed this and this is right because, the dynamic type system caught it. So I would personally go with untyped.
Oh, thank you.
Can you talk about the decision to start with delimited continuations rather than undelimited continuations as a layer, or maybe just upward only or downward only continuations before moving to general undelimited continuations?
This is an interesting question. So I learned the limited continuations first, and I think that it's easier to understand them undelimited continuations because if you use control operators like call CC, you are not only dealing with continuation, but also there's the notion of aborting, and that is hard for beginners. I think so if you use the limited control operators, you can just treat continuation like ordinary functions, which students already know. So I think the limited continuation is easy.
Thank you.
Hi, Audrey So from the University of Washington. I think that this is a great idea. I also wish that we had something like this for monads, although I feel like a lot of people would just tell me to learn Haskell. But anyway, yeah, I was wondering if you had any ideas about like what kind of modalities or like applications or like where would you host this language? Like, would you want it to have like, I don't know, be running in like a Jupyter notebook almost sort of thing on the web, or like have your own like Dr. Continuations language?
Yeah, I'm thinking of something like Dr. Continuations. So like the Dr. Racket environment, you have all the tools in a single editor. Yeah.
Yeah. Okay. Thank you.
Also, it would be nice if it can be run in a browser, right?
Yeah, like I don't know. I'm more familiar with the realm of theorem provers, and apparently Lean has something running in the web, and a lot of people have been using that and like playing around with it. So, and there have been a lot of successful web programming language. Like I don't know how successful, like in long-term outcomes, but a lot of really cool tools that are based in web technologies. So I don't know, just something to look into.
Yeah, thank you.
Yep.
All right, well, let's thank our speaker one more time.
Thank you.
Thank you, Yu. All right. Well, I believe that concludes our third and final SCHEME workshop session of the day. I'm going to take, once again, the chair's privilege to mention if anybody had finished, submitted a paper, and wanted to resubmit an archival version. There so happens to be a TFP conference coming up in November, and I happen to know somebody who's organizing it would welcome your submissions. And other than that, I think I'll turn it back over to Marco for any final thoughts of the day.
Well, thank you everybody for coming. I trust that I will see all of you in Milan the next year, right? Okay. And Christos, thank you for the wonderful talk. That was really, really good. And I want to thank all the authors for doing it. Okay.
Thank you, Marco, for the wonderful SCHEME workshop. Yeah, there's almost certainly a quorum. Oh. I'm not going to be able to get there tonight because I've got a plane leaving. But if anybody wants to get together for dinner this evening, I know Will Bird also mentioned wanting to get a SCHEME quorum together, and I think Andy Keep said he was going to be around for the dinner afterward.
Yeah, should we maybe meet at 5 o'clock outside here, just outside the school?
Yeah. Okay. Anybody who wants to SCHEME, meet out here at 5 o'clock, and I'll pass the word on to Will.
Yeah, and we'll just find a place. Before we disperse, can I say something? I want to announce that we have a new DSL out. Does it work? Yeah. Okay. I want to announce that we have a new DSL out for teaching NP-hard reductions. It's called Haslang Carp. It's available through Racket's package system. You just download it, install it as a normal package. It has a Rosette backend. If you or some of your colleagues are interested in adding some programming into their Intro to Algorithms classes, and they teach NP-hard reductions, which is a very difficult topic, please consider it. There is also a paper that was out at PLDI 2022 that basically describes the principles behind the design of the language. Thank you.